Welcome back to Sleep Nova. Sit back, relax, and don't forget to comment where you're watching from down below. It's amazing seeing people all around the world supporting my small channel. Now, enjoy the show. We begin in darkness. Before any star set the heavens alight, before any galaxy took shape, there was a deep and endless night. We remember it, the universe in its infancy, all energy and matter spread thin, yet no light to break the blackness. In that primeval silence, there were no stars, no galaxies, only a cooling fog of hydrogen gas, invisible and waiting. The cosmos was dark, and it would remain so for ages, a vast ocean without islands, a night without memory. Yet even in that darkness, the seeds of light were present. Tiny ripples of gravity, left by the birth of the universe itself, were drawing matter together, slowly, silently. In the void, unseen clouds of gas and halos of mysterious dark matter gathered and grew denser. Time hardly had meaning in this eternal midnight. But at some point, perhaps a few 100 million years after the beginning, change arrived. In pockets of the darkness, the first fires kindled. Deep in those dense halos, gas clumped until pressure and heat ignited the first stars. One by one, brilliant newborn stars pierced the cosmic night like embers in a vast, dark sea. Their light was faint at first, much of it absorbed by surrounding clouds, but it grew. More stars burst into existence, and around them began to form the first primitive galaxies, a cosmic dawn after the long darkness. We remember the moment the lights came on. A firestorm of star birth swept through the young universe, the first galaxies assembling as clusters of glittering light. What had been an endless silent dark became a realm of scattered gleams. Imagine it, the newborn cosmos, less than 1 billion years old, sprinkled with the glow of infant galaxies. Each was like an island universe adrift in a black sea, isolated and alone, yet bravely shining. These first galaxies were much smaller and simpler than the grand spirals and ellipticals that would follow. They flickered pale and red, their light stretched and dimmed by eons of travel. But however faint, they were beacons, the first organized realms of stars, announcing that the long cosmic night was ending. From where we stand now, nearly 14 billion years later, we can still catch glimpses of those early faint galaxies with our most powerful telescopes. They appear as tiny smudges of light in deep field images, ghostly and ancient. Many have long since grown or merged or dissipated, but their ancient glow still travels the universe, telling the story of when the cosmos first lit its candles. In that epoch, the universe was only a few % of its current age, a toddler cosmos taking its first steps into illumination. The darkness fought to hold on, absorbing and scattering the first starlight. But starlight is persistent. It ionized the fog around it, burning holes through the murk. Gradually, the black curtain lifted. What had been a cold, neutral haze became a transparent window. The era astronomers call the cosmic dark ages yielded to the cosmic dawn. We, the living cosmos, remember this transition. It was the first time light had structure and form. It was the moment the universe began to perceive itself in the mirror of starlight. The first galaxies were the universe awakening to its own possibilities, each a tiny island of something rather than nothing. In those islands, countless suns would soon forge heavier elements, explode, and seed space with the ingredients for planets and life. The story of everything we know, stars, planets, potential life, began with that emergence of galaxies from darkness. Out of utter night came the glimmer of countless distant candles. This was the threshold of galactic dawn. Out of the void came light and pattern, as if the cosmos had dreamed in darkness and now opened its eyes. Scattered across unfathomable distances, the infant galaxies shone alone, unaware of one another, like solitary lighthouse beams sweeping an empty sea. They were the first galaxies, precious, solitary sparks in a silent abyss. The universe, once a slumbering expanse of night, was now awake with faint starlight. In that fragile glow, the cosmos beheld its reflection for the first time. A mysterious, reverent hush falls over us as we recall this dawn, the moment we first illuminated the darkness, the moment when galaxies, and with them the seeds of everything to come, emerged and took their place in the vastness. Now, in the wake of that first dawn, we turn our gaze to a single galaxy to understand the wonders it holds. Each galaxy is a vast cosmic island, and like any island, it has its own geography and inhabitants. Picture one such island universe, perhaps like our own Milky Way. It is a great swirling city of stars. Hundreds of billions of suns blaze within it, swarming in a rotating disk like a giant glowing whirlpool. Gravity is the architect that binds this galactic city. It gathers stars by the billions and holds them in its grasp, preventing them from drifting into the void. When we look at a galaxy through a telescope, we see the collective glow of all those stars merged together. A luminous disk or an ellipse or an irregular scatter of light. But within that glow lies structure, bright knots and cloudy bands that reveal the galaxy's anatomy. At a galaxy's center resides a dense concentration of stars, a nucleus or bulge. In a spiral galaxy, surrounding this bulge is a flat disk spreading tens of thousands of light years, where stars, gas, and dust orbit in orderly rotation. The disk often bears spiral arms, winding structures that pinwheel out from the center. These arms are not solid arms of material, like spokes. They are regions of slightly higher density that move around the galaxy more slowly than the stars and gas. As stars and gas orbit, they bunch up in these density waves, rather like cars piling up in traffic on a highway. The compression of gas in spiral arms triggers the birth of new stars, which is why the arms are studded with bright blue stars and pink nebulae, the telltale signs of ongoing star formation. Between the arms, older stars orbit more quietly. The galaxy's outskirts are generally fainter, with fewer young stars and less gas. Above and below the disk lies the halo, a sparse, spherical realm of very old stars and globular star clusters, tight, ancient stellar congregations, orbiting the galaxy's center in all directions. And permeating all these components is a massive halo of invisible dark matter, of which more later, extending far beyond the visible edge, whose gravity holds the galaxy together. Let us tour these components in turn. First, the stars. They range from hot, young blue giants that burn briefly in the spiral arms, to cool, red, ancient stars that populate the bulge and halo. Each star is a sun with its own potential family of planets. The number of stars is staggering, 100 billion or more in a large spiral. If we could fly through the galaxy, stars would surround us like a glittering snowstorm, especially near the core, where they crowd close. But even in the outskirts, you'd never be far from a sun. Despite that, the distances are so vast that to an individual star, like our sun, its nearest stellar neighbors are several light years away, tiny points separated by great voids. A galaxy is mostly space, but the sheer number of stars fills that space with collective light. Next, the gas and dust. Strewn through the disk are immense clouds of gas, mostly hydrogen, and interstellar dust grains. This material is the raw ingredient for new stars. In a galaxy's spiral arms, these clouds are numerous and concentrated. Between arms, they are sparser. Dust, though only a small fraction of the galaxy's mass, has an outsized effect on appearance. It absorbs and reddens light. Along the Milky Way's plane, we see dark rifts where dust in nebulae blocks the light of background stars. Gas, on the other hand, often reveals itself by the light of stars embedded within it. For example, glowing ionized hydrogen clouds, H2 regions, that appear as pinkish patches, marking sites of current star formation. Surrounding the bright disk of stars and the faint glow of gas is something more elusive. Every galaxy is embedded in an enormous halo of invisible matter, dark matter. We call it dark because it emits no light. We infer its presence by its gravitational pull. This unseen halo outweighs all the stars and gas by a factor of 5 or more. It extends well beyond where the visible galaxy fades out, like a transparent sphere engulfing the luminous parts. Were it not for the dark matter's gravity, galaxies as we know them could not hold together. The outer stars would fly off, and the galaxies we saw form in the early universe might never have coalesced so quickly. Finally, many galaxies harbor an immensely dense object at their core, a supermassive black hole. In a typical large galaxy, this central black hole might be millions or billions of times the mass of our Sun, confined to a region no bigger than our solar system. It's an almost inconceivable concentration of mass. Most of the time, this black hole is relatively quiet, seen only indirectly, for instance through stars orbiting it at high speeds. But if gas funnels into it, the black hole can become a quasar or active galactic nucleus, blazing with energy and even shooting out jets. We will revisit this phenomenon later. All these components, stars, gas, dust, dark matter, black hole, together make up a galaxy's anatomy. They are bound by the invisible glue of gravity, moving in a cosmic choreography. The stars orbit in the galaxy's gravitational field. In a spiral disk, they move in circular orbits around the center. In an elliptical, they swarm in random elliptical paths. In the halo, they soar in elongated trajectories far above or below the disk before falling back. The gas flows in the disk, sometimes shocked into new patterns by spiral density waves or supernova blasts. The dark matter halo itself likely just provides a steady gravitational background, as it does not clump into stars. From afar, a galaxy may look serene, like a single smear of light, or a softly glowing ellipse. Up close, it is bustling with activity, stars being born and dying, gas clouds drifting and colliding, clusters orbiting, perhaps a black hole gently accreting matter or flaring. It is a dynamic breathing system. The beauty we see, those graceful spiral arms or that smooth elliptical light, is the composite of billions of individual lives and events playing out on colossal scales. In many ways, a galaxy is a cosmic ecosystem, with stars as its organisms, gas as its sustenance, black holes as both regulators and recyclers. Gravity holds it all in a delicate balance. Consider again our hypothetical traveler flying through a galaxy's disk. In the densest regions near the core, the sky would be awash with starlight, thousands of brilliant suns glittering in a small patch of sky, far more spectacular than any night on Earth. In the outskirts, the stars thin out. The night would grow darker, though the majestic band of the galaxy's plane would still stretch across the sky, a reminder of the greater structure one inhabits. If our traveler ventures further, above the disk into the halo, the view would shift. Most of the galaxy's stars would lie below like a flat, glowing spiral, and around the traveler, there might only be the sparse halo stars, and perhaps a globular cluster or two in the distance, lonely outposts of the galaxy far from its busy heart. This is the anatomy of a galaxy, a vast ensemble of matter arranged by gravity into a structure that is at once orderly in its overall shape and orbit patterns, and chaotic in the micro-detail of individual star motions and gas turbulence. It is a self-contained cosmos, with internal processes of creation and destruction set against the backdrop of the expanding universe. Not all galaxies are alike, however. As galaxies grew and interacted, they assumed diverse shapes and characters. Some became elegant spirals, others grew into sprawling ellipticals, and many smaller ones took on irregular, whimsical forms. In the grand cosmic menagerie, galaxies are as varied as the creatures in a primeval sea, spiraling, stretching, colliding and twisting into different configurations. Their shapes are visible signposts of their histories. Spiral galaxies are the archetype we've already been exploring. They have pinwheel shapes, a flattened rotating disk with spiral arms, a central bulge, and often a bar of stars slicing through the bulge. Our Milky Way is one such barred spiral. Spirals are galaxies in their star-forming prime. Their arms, shining with young blue stars and dotted with pink emission nebulae, show that these galaxies still have plenty of gas to make new stars. The presence of dust in the disk creates dark filamentary lanes that outline the spiral structure when viewed face-on, and that give edge-on spirals a shadowy mid-plane. 2/3 of spirals, including the Milky Way, have a bar structure, which is thought to redistribute material and perhaps trigger star formation by funneling gas inward. Spiral arms can be tightly wound or more open and irregular. Some spirals, called grand design, have well-defined arms that can be traced almost a full circle around, while others have fragmentary arm segments. Regardless of exact form, the hallmark of a spiral is a mix of star ages, hot young stars in arms, and older stars in the bulge and extended disk, and an ongoing cycle of star birth. Elliptical galaxies have a very different look. They range from nearly perfect spheres to elongated football shapes. Ellipticals typically show no spiral structure, no disk, and crucially, almost no cool gas or dust. Thus, they lack the neon signs of star formation, no blue young star clusters or glowing nebulae. Instead, their light is dominated by older reddish stars. An elliptical galaxy often appears as a smooth gradient of light, brightest at the center and dimming uniformly outward, with little texture. The stars in ellipticals orbit in random directions, like bees in a swarm, unlike the coherent rotation in a spiral's disk. This suggests ellipticals likely formed by mergers of smaller systems. Imagine two spirals merging. Their ordered disks could be scrambled into one big cloud of stars, orbiting every which way. The largest galaxies in the universe are giant ellipticals found in cluster centers, which probably grew by consuming many smaller galaxies. Conversely, there are also tiny ellipticals, and dwarf spheroidals, only a bit bigger than globular clusters, often companions to larger galaxies. Without much gas, ellipticals have long since ceased meaningful star formation. They are largely in a passive, quietly shining state. Lenticular galaxies, SRO type, are something of a bridge between spirals and ellipticals. They have a disk, like spirals, often with a central bulge, but no spiral arms and very little gas or dust. A lenticular galaxy looks like a smooth disk or a bulge with a faint pancake around it. One might think of them as armless spirals or disk ellipticals. They likely form when a spiral galaxy uses up or loses its gas. For example, gas stripped by falling into a cluster or exhausted by star formation and feedback. The result is a galaxy that still rotates and has a disk structure, but no spark left to form new stars. Lenticulars often show dust lanes or rings, but no active HII regions. They tend to have intermediate colors, not as blue as star-forming spirals, not as red as ellipticals, although more toward the yellow due to aging stellar populations. If spirals are galaxies in their adulthood and ellipticals in old age, lenticulars are perhaps late middle age. The shape remains, but the youthful glow is gone. Irregular galaxies are those that defy the standard categories. They have no regular shape, neither a disk with arms nor a smooth ellipsoid. Many are small, dwarf irregulars, essentially blobs of stars and gas. They often contain significant amounts of gas and ongoing star formation, but in a haphazard pattern. The large and small Magellanic Clouds, visible to the naked eye from the southern hemisphere, are irregular dwarf galaxies orbiting the Milky Way. The Large Magellanic Cloud, LMC, actually has a bar and one spiral-like arm, It's a magpie of a galaxy, part bar, part irregular disk. The small Magellanic Cloud is more chaotic, an amorphous sprinkle of stars with no obvious center. Such irregulars could be young galaxies that haven't settled into a definitive form, or were perhaps normal galaxies distorted by gravitational encounters. Some irregular shapes result from collisions. For instance, the aftermath of two galaxies grazing each other might be an irregular burst of stars. There are also ring galaxies and other peculiar forms, like the cartwheel galaxy's bullseye shape, usually arising from special interactions. Irregulars demonstrate that galaxy formation can be messy. They remind us that not every galaxy gets to be a neatly structured spiral or a smooth ellipse. Some are cosmic driftwood, fragments still finding their form, or scraps left over from bigger systems. In truth, many galaxies evolve from one type to another. A spiral can merge with another and become an elliptical. A tidal encounter can turn a spiral into a distorted irregular, perhaps temporarily, before it resettles. Two dwarfs colliding might spark a mini-spiral structure. The classification is a snapshot of a galaxy's visible state, but underlying that state is a story. Even so, Hubble's classic tuning fork diagram, spirals branching into barred and unbarred, lenticulars in the middle, ellipticals on the handle, remains a useful map of galaxy diversity. Each shape speaks to physical conditions. Spirals mean a spinning disk with ongoing star formation. Ellipticals mean a gravitationally relaxed system that likely experienced mergers and lacks fuel. Irregulars often mean either youth or disruption. Across the cosmos, we see that early on, many galaxies were irregular and clumpy. Over time, through mergers and accretion, some settled into spirals. Others, especially after big collisions, became ellipticals. Thus, the shapes we categorize are also stages in a galactic lifetime, or outcomes of galactic interactions. Different shapes also affect what life inside might be like. A planet in an elliptical galaxy's outskirts might have a night sky filled only with a gentle, diffuse glow. No grand Milky Way band, since the stars are more uniformly distributed. In a dwarf irregular, the sky might be relatively dark, except where a local pocket of star formation lights it up. In a spiral like ours, we enjoy the spectacular band of the Milky Way and rich constellations, a product of living in a structured, starry disk. Yet beneath these varied forms, galaxies share a fundamental role. They are star factories. No matter the shape, virtually every galaxy at some point converts gas into stars. This ongoing creation process is the heartbeat of a galaxy's life. Let us turn to that internal activity common to all but the most dormant galaxies, the birth of stars within these island universes. Galaxies are cosmic furnaces where new stars are forged from interstellar gas. Deep within vast, cold molecular clouds in a galaxy's disk, gravity gathers pockets of gas until they ignite into stars. This happens continually in galaxies with available fuel. Spirals are especially prolific. They're giant molecular clouds, often tens or hundreds of light years across, and containing thousands of solar masses of molecular hydrogen, serve as nurseries for star clusters. Within such a cloud, small density enhancements draw in gas around them. As the gas compresses, it heats up. When a pocket, perhaps a few tens of times the sun's mass, collapses enough, the temperature and pressure at its core soar to the point that hydrogen nuclei begin to fuse into helium. At that moment, a star is born. A tiny thermonuclear furnace balancing gravity's inward pull with energy's outward push. The newborn star often emerges in a cluster with dozens or hundreds of siblings, all formed from the same cloud. The remaining gas may be blown away by the collective radiation and winds of those newborn stars, clearing out a bubble and leaving behind a shining cluster. Throughout a galaxy's spiral arms, this drama plays out in countless locales. For example, in our Milky Way, the Orion Nebula is one such stellar nursery. To the unaided eye, Orion's sword shows a faint fuzzy patch. Through a telescope, it's a glowing cavern of gas with a handful of massive young stars illuminating it. Those stars are mere infants, less than 1 million years old. And where we see the nebula's bright veil, many more protostars are likely gestating. The Orion Nebula is just one of many star-forming regions in our galaxy's Orion Arm. Star formation rates vary. The Milky Way forms roughly 1 to 2 sun-mass stars per year. In fact, mostly lower-mass stars. The high-mass ones are rarer. Some galaxies, especially in earlier cosmic times or in violent starbursts, form stars much faster. There are galaxies observed, often due to collisions or mergers, forming perhaps 50 or 100 suns per year for short periods. We call these starburst galaxies. They blaze with the light of massive young stars and are often veiled in dust that those same stars later blow away. Conversely, small dwarf galaxies or massive gas-poor galaxies might only trickle out a star or two per year, or nearly none if they've lost their gas. Galaxies self-regulate this star formation to an extent. When many stars form at once, the first massive ones, O-type stars, emit intense ultraviolet radiation and charged particle winds. They heat and push on the surrounding gas. Shortly thereafter, within a few million years, some of those massive stars explode as supernovae, sending shockwaves through the molecular cloud. These effects can compress some parts of the cloud, triggering more stars in a chain reaction, but can also disperse other parts, shutting down further star formation in that region. In a spiral arm, one often sees this sequence like a ripple. Moving along the arm, there's a dust lane, where gas is gathering, then bright emission nebula, where stars have just formed, then star clusters with no nebulae, the gas blown away. It's a beautiful choreography. The galaxy's rotation and wave pattern orchestrate cloud collapse, and the newborn stars then orchestrate cloud destruction, limiting the yield. Over a galaxy's lifetime, this cycle steadily transforms gas into stars. In doing so, it also enriches the galaxy with heavy elements. The first generation of stars in a galaxy may have been born from nearly pristine hydrogen and helium left from the Big Bang. They lived and died, manufacturing heavier elements in their cores and in supernova explosions. Those metals, astronomers call all elements heavier than helium metals, mixed into the galaxy's gas. Later stars then formed from slightly enriched gas, and so on. Thus, as the galaxy ages, its gas and new stars contain higher fractions of elements like carbon, oxygen, silicon, iron, the very elements that make rocky planets and ultimately biology possible. Our Sun, born about 4.6 billion years ago, is metal-rich. About 2% of its mass is elements heavier than helium, evidence that it is a late-generation star. The earlier generations, now long gone, bequeathed the ingredients that went into the Sun and Earth. In this sense, galaxies are not just star factories, but also chemical factories, minting the periodic table as they go. The star formation process in galaxies will continue as long as there is cold gas to convert. But gas is a finite resource within a galaxy. It can be used up, or expelled, or locked in stars. Large galaxies can sustain moderate star formation for many billions of years, while small dwarfs may consume their gas quickly or have it stripped away by interactions. When we look at galaxies, their colors give away their star-forming status. Blue-tinted galaxies are actively forming stars. Short-lived blue stars tint the light, whereas yellow-red galaxies have little star formation, their light dominated by long-lived reddish stars. Many spirals have blue spiral arms but a yellowish bulge, indicating active star formation in the disk, but an older population in the core. Ellipticals are uniformly yellow-red, having long ago ceased making stars. Our Milky Way, with its mix of blue and white along the arms and a yellowish center, tells us it's still in business as a star factory, though not a starburst by any means. In its suburbs, like our Sun's vicinity, new stars form at a leisurely rate. In contrast, Consider a galaxy like M82, the Cigar Galaxy. It's undergoing a ferocious starburst likely triggered by interaction with its neighbor M81. In M82's core, stars are forming so rapidly that their combined winds and supernovae are blowing gas out of the galaxy in colossal superwinds, visible as filamentous outflows. It's a galaxy essentially heaving with the effort of birthing stars, and in doing so, it may be burning through its available gas in a cosmic blink, tens of millions of years, after which it will calm down, having spent its fuel. Thus, star formation is the heartbeat of a galaxy, sometimes steady, sometimes rapid and irregular. With each beat, new stars light up, and with them new possibilities, perhaps planetary systems, perhaps life. Every star we see in the night sky, aside from a few exceptions like supernovae, is evidence of this ongoing heartbeat. Our own existence is tied to it. The Sun is a product of the Milky Way's star-making abilities, and our planet's raw materials were forged in previous stars. One day, far in the future, the Milky Way and other galaxies will run low on gas. Star formation will slow to a trickle and eventually almost stop, as we'll discuss when we consider galaxies aging. But for now, in this epoch, the universe is still rich with galactic star factories. Each pinprick of light in a distant galaxy's photograph could be the home of millions of newly formed stars or stellar systems coming into being. In a very literal way, galaxies create the light that fills the universe. They are the engines turning dark, cold gas into brilliant starlight, generation after generation. They have been doing so since the cosmic dawn, and the cumulative light of all those newborn stars over the eons has gradually lifted the universe out of darkness. While stars are being born throughout a galaxy's disk, another drama is unfolding in the galaxy's core. At the center of most galaxies, as we noted, lies a supermassive black hole. In quiet times, this black hole is an invisible presence, detected only by its gravitational influence. But when it feeds, it can outshine the entire galaxy and radically affect its surroundings. The interplay between galaxies and their central black holes is a vital theme in cosmic evolution. We find that the mass of a central black hole is closely correlated with the mass of the galaxy's bulge in spirals, or overall stellar population in ellipticals. For instance, our Milky Way's black hole is about 0.01% of the galaxy's total stellar mass, and that fraction holds similarly for many others. This hints that the growth of black holes and the growth of galaxies went hand in hand. They know about each other. How could that be? The answer is feedback. When a galaxy's black hole accretes a lot of gas, it enters an active phase, becoming what we call an active galactic nucleus, AGN, which in extreme cases is a quasar. In this phase, the region around the black hole emits tremendous energy. Gas spiraling into the black hole forms a superheated accretion disk, shining across all wavelengths. Magnetic fields can tap into the rotational energy and funnel some plasma into enormous jets that shoot out of the galaxy's center at near light speed. Meanwhile, intense radiation pressure from the disk pushes outward on the surrounding gas. In effect, the feeding black hole blows a cosmic wind. This energy output can have profound effects on the galaxy. It can heat the interstellar gas or even expel significant portions of it from the galactic nucleus. If the black hole's output is powerful enough, it can sweep the galaxy's bulge nearly clean of the cold gas needed for star formation. This is one way star formation can be quenched in a massive galaxy. The quasar or AGN phase pumps energy into the galaxy and halts the supply of cool gas. The black hole's growth thus self-regulates. Once it becomes very luminous, it curtails further fuel from reaching it and also shuts down new star birth in the inner galaxy. This is why we don't see galaxies with ridiculously overmassive black holes compared to their size. The black hole will have effectively shut itself off by clearing out its vicinity. During the early active times, the galaxy black hole duo can be spectacular. Quasars, seen in the young universe, were galaxies with incredibly bright cores, often disturbed or merging in appearance, suggesting that interactions funneled large amounts of gas to their centers, igniting both starbursts and quasar activity. These quasars likely blew out so much gas that their host galaxies soon ran out of fuel for both star formation and further black hole feeding. The quasar then faded, and the galaxy was left as a more passive, elliptical, or lenticular, full of old stars and with little gas, a veteran of a violent youth. Even in less extreme cases, we see AGN feedback at work. In clusters of galaxies, the central galaxy often shows signs that its black hole periodically inflates huge bubbles in the surrounding hot gas, observed as cavities in X-ray images. These bubbles rise and send gentle shockwaves into the cluster, preventing the hot gas from cooling down to form new stars. The black hole is effectively heating the environment enough to forestall a cascade of star formation that would otherwise happen as the cluster gas cooled. This phenomenon is observed in the Perseus cluster, Virgo cluster, and others, where beautiful filamentary structures in the hot gas correspond to past outbursts from the central AGN. Our own Milky Way's black hole, Sagittarius A, is currently faint. Its accretion disk is trickling only a bit of material. But not so long ago, cosmically speaking, it likely had a blazar-like episode. The Fermi bubbles, giant lobes of high-energy emission, extending 50,000 light-years above and below the galactic center, are thought to be remnants of an outflow from Sagar A, perhaps a few million years ago. They testify that even a relatively small supermassive black hole can drive galaxy-scale phenomena when active. Thus, a galaxy's central black hole can be seen as a sort of power regulator. During formative times, it lights up and, through its winds and radiation, keeps the galaxy from overdoing star formation. Eventually, the galaxy and black hole reach an equilibrium. The black hole no longer has a deep reservoir of gas to feast on. Star formation slows down, and they settle into a quieter phase. When we observe a massive galaxy today that isn't forming stars, often we find a quiet but hefty black hole at the center, exactly as this co-evolution scenario predicts. It's remarkable. Something as tiny, in size, as a black hole's accretion disk can influence a whole galaxy tens of thousands of light-years across. It's like a gear in a clock, small but key to the whole mechanism. Black hole feedback provides a link between the very small, sub-parsec scales and the very large, galactic scales. Through it, the cosmos achieved a balance. Without it, models suggest galaxies would be too large and too blue, forming stars far longer than observed. With it, galaxies mature and stop growing after a point, aligning with what we see. In cosmic terms, we can imagine a kind of dialogue. As a galaxy's gas collected and stars formed, the central black hole grew. When the black hole became powerful, it said, "Enough," and blew out the remaining gas, both halting further star formation and starving itself. The galaxy, having been energetic and blue, became a more quiescent reddish system. We see the aftermath of this in the present universe's many red ellipticals and lenticulars. Our own galaxy hasn't undergone a major quenching. It's moderate in mass, but in about 4 billion years, when the Milky Way merges with Andromeda, our central black hole will likely feast on a lot of inflowing gas and could briefly become a quasar, perhaps helping to shape the merged galaxy that will result. Thus, the presence of central black holes and their ability to transform energy make them crucial to the story of galaxies. In youth, galaxies shine by the grace of star formation. In their energetic adolescence, some shine by the grace of an AGN. By old age, both processes wane, leaving a quietly shining population of stars and a dormant heavy heart at the center. Galaxies and their black holes are partners in this cosmic evolution, each influencing the other. Galaxies are not static islands. They are dynamic entities that are born, grow, and change over the vast history of the universe. From the first protogalactic fragments after the Big Bang to the majestic spirals and ellipticals we see around us today, galaxies have undergone significant evolution. They have accreted matter, collided and merged with one another, and transformed from active star-forming systems to, in many cases, quiescent assemblies of old stars. The story of a galaxy's life is written in its shape, its star content, and its motion. It's a biography spanning billions of years. In the beginning, as we recalled, the earliest galaxies formed when the universe was very young. They likely started as small clumps, dwarf galaxy-sized pieces drawn together by dark matter gravitational wells. These clumps were full of gas, which began forming the first stars. Early star formation might have been frantic, massive stars, short-lived, quickly enriching the surroundings with heavier elements upon exploding. Small clumps merged into bigger clumps. Through both chaotic mergers and smoother accretion of gas along filaments of the cosmic web, galaxies began to build up. Simulations of cosmic structure show that little galaxies, with masses perhaps 1,000,000 to 1,000,000,000 times that of the Sun, formed first and then congregated to form larger ones. This process is sometimes called hierarchical assembly, like small bricks assembling into bigger structures. Our Milky Way, for example, has cannibalized many smaller systems over time. It contains star streams and outer clusters that are the remnants of devoured dwarfs. Even now, it's shredding the Sagittarius dwarf spheroidal galaxy, adding those stars to its halo. In the past, it likely did this multiple times. This is how a large spiral can grow over billions of years. Galaxies also grew by accreting fresh gas from their surroundings. In the early universe, gas was more densely and readily available, and galaxies could draw in cold flows from intergalactic space, sustaining high star formation rates. Around 2 to 3 billion years after the Big Bang, roughly the peak of cosmic star formation, often called cosmic noon, many galaxies were in a veritable growth spurt, rapidly forming stars, growing their black holes, and often interacting with neighbors because the universe was smaller then. Everything was closer together. Collisions and mergers are a dramatic driver of galactic evolution. When two galaxies merge, their shapes are profoundly altered. If a small galaxy merges into a big one, a minor merger, the big one mostly keeps its identity. Perhaps the event thickens the big galaxy's disk, or flings some of the small galaxy's stars into the halo, or triggers some extra star formation. But when two comparably sized galaxies merge, a major merger, the result tends to be an elliptical galaxy. The violent relaxation of stars' orbits during the merger randomizes their motions, and any cold gas present can be either consumed in a burst of star formation or expelled by feedback. Thus, the end product is an elliptical with little gas. Major mergers also tend to grow the central black hole efficiently, since gas is funneled to the center, possibly igniting a quasar that then blows out the remaining gas. We believe many of today's giant ellipticals formed from such major mergers billions of years ago. Not every galaxy undergoes a major merger, though. The most massive ellipticals likely did, some multiple times. But many spirals, including perhaps our Milky Way, have had a relatively gentle history with only minor mergers. Such galaxies can retain their disk structure and continue forming stars gradually. The Milky Way has a mix of populations that tell its history. A thin disk of younger stars, a thicker disk of older stars, perhaps heated by past interactions, a halo of very old, metal-poor stars, some possibly from small galaxies it absorbed early on, and a central bulge that could be the result of an ancient merger or internal evolution of the disk through bar formation. Galactic evolution is also about the decline of available gas. Initially, galaxies had lots of fuel. By now, many have used much of it up or locked it in stars. As a rough trend, the universe's star formation rate has declined over the last 10 billion years. Large surveys of galaxies find that those in the past were, on average, forming stars at a higher rate than comparable galaxies today. This aging of galaxies means that the cosmic color palette has shifted. In the past, galaxies were bluer, more hot young stars, whereas today, a larger fraction of galaxies are red and dead. Environment plays a big role too. A galaxy in a rich cluster might have been quenched earlier. The cluster's hot gas can strip the galaxy's cold gas as it moves, a process called ram pressure stripping, and frequent encounters can stir up the galaxy and cause it to lose its orderly disk structure. Indeed, cluster galaxies are dominated by ellipticals and lenticulars, suggesting that many spirals that fell into clusters lost their gas and transformed. On the other hand, galaxies in lower density environments, small groups or voids, have fewer interactions and often retain their spiral structure and star-forming ability longer. Our local group, containing the Milky Way, Andromeda, Triangulum, and many dwarfs, is a fairly low-density environment. We have evidence that neither the Milky Way nor Andromeda has had a major merger in the last 9 to 10 billion years, allowing them to remain spiral galaxies. However, they are on course to merge with each other in about 4 to 5 billion years. When that happens, the result will likely be a more elliptical-like galaxy, sometimes nicknamed Milkomeda. Star formation may initially spike during the collision as gas clouds slam together, but eventually, much of the gas will either be used up or thrown out, and star formation will wind down. The merged galaxy will settle as a large, somewhat elliptical system with a very different night sky for any inhabitants. No clear disk band, perhaps just a diffuse glow of a central core, and an extended halo of stars. So the future of galaxies is, in a sense, written by their interactions. Over very long timescales, say 100 billion years or more, the continued merging of groups and clusters means many galaxies will coalesce into a few very large galaxies, especially as cosmic expansion drives distant ones out of reach. There's a concept that eventually gravitationally bound structures like our local group will merge into one giant galaxy, and beyond that, thanks to the accelerating expansion of the universe, that galaxy will be essentially alone, all other galaxies having receded beyond the observable horizon. But that far future scenario is speculative and far beyond any current age. In summary, the galaxy we see today is the product of billions of years of change. A spiral like the Milky Way was once smaller, likely a swarm of proto-galaxies coming together. It has grown by accretion and mergers, formed stars steadily, and will continue to change, especially with the impending Andromeda encounter. An elliptical in a cluster may have once been several disk galaxies that danced and combined. Even tiny dwarfs have stories. Some might be leftover building blocks that never made it into a larger structure, living fossils of the early cosmic times. Galaxies, therefore, have life cycles. They can be thought of in terms of birth, formation from primordial matter, growth, star formation and mergers, maturity, a steady state, often disk galaxies with ongoing star formation, and old age, exhaustion of gas, becoming passive. Not every galaxy neatly follows this, and some experience rebirth if new gas is acquired, but many do traverse from active to quiet. Our universe today contains galaxies in all these stages. When we look out in space, distance corresponds to looking back in time. Nearby, we see many ellipticals and gas-poor systems, galaxies that have largely completed their star-forming story. Far away, hence long ago, we see more irregular, clumpy galaxies furiously forming stars, the youth and adolescent stages. By combining those views, we piece together the saga of galactic evolution. Now imagine the large-scale arrangement of these galaxies. They are not scattered randomly like isolated birds. They congregate and form patterns on the grandest scales. Galaxies, along with galaxy clusters and superclusters, are woven into a cosmic web, a filamentary network that spans the observable universe. This is the imprint of the initial tiny density fluctuations from the Big Bang, amplified by gravity over billions of years. If we could zoom way out, far beyond our local group, beyond our local supercluster, we would see galaxies arranged in filaments and sheets, intersecting at dense nodes, clusters, with immense voids in between where few galaxies reside. This we call the cosmic web. It looks somewhat like a three-dimensional spiderweb or foam. Each filament might stretch hundreds of millions of light years and contain many groups and clusters of galaxies. At their intersections sit the richest clusters, like the Coma or Virgo clusters, teeming with thousands of galaxies. Between filaments are voids, huge cavities, 100 million light-years across or more, that have only a sprinkling of galaxies, truly cosmic emptiness. Our Milky Way inhabits a minor filament on the outskirts of the Virgo supercluster. Recently, astronomers gave our local supercluster the name Laniakea, meaning immense heaven in Hawaiian. We are pulled gently toward the dense center of Laniakea, the region of the Virgo cluster, but will likely never reach it due to the expansion of the universe acting on larger scales. The local group itself is a little cluster on a filament that extends out toward other nearby groups, like the M81 group and the Centaurus group, all on the boundary of the Virgo supercluster complex. This cosmic web is mapped by surveying galaxies and noting their 3D positions. One famous survey, the Sloan Digital Sky Survey, created maps with over 1 million galaxies, revealing an astonishing foamy structure. Long filaments and walls, like the Sloan Great Wall, a filament 1.4 billion light-years long, and huge voids such as the Bootes Void, where few galaxies dwell. It's fascinating to realize that on scales of billions of light-years, galaxies themselves are like atoms, gathering into these massive structures. Gravity is the sculptor of the cosmic web. Dark matter, which does not interact directly with light or normal matter except via gravity, began clumping first, forming a filamentary network under the influence of its own gravity. Normal matter, gas, fell into those dark matter structures. Wherever the dark matter density was highest at filament intersections, galaxies and clusters eventually formed from the cooling gas. Along the filaments, chains of galaxies emerged. In the voids, the paucity of matter left vast expanses nearly empty. One might imagine flying through the universe on these scales. For long stretches, you would traverse dark, relatively empty void, maybe passing an occasional lone galaxy or small group that inhabits a shallow density well. Then gradually, galaxies would appear more frequently, like approaching a metropolitan region. You might enter a filament. Around you, galaxies would pepper space in every direction, often clumped in groups. Further on, you could come upon a node, a cluster like Coma, where hundreds of galaxies swarm like bees in a hive, the ambient X-ray glow of hot gas suffusing the cluster. Exiting on another side, a filament might lead you onward to another cluster or spread out into a wall, a sheet-like arrangement dozens of megaparsecs wide, but relatively thin. To the human eye, of course, none of this structure is directly visible. We see it only by plotting galaxy positions. But an observer within a rich filament would see many galaxies in their night sky. Some might even be naked-eye bright if they're close enough, the way Andromeda is visible from Earth. In the heart of a cluster, the sky would be crowded with fuzzy glows of elliptical galaxies and maybe intense light from a central CD galaxy. In a void, the night sky might have far fewer galaxy smudges visible at all. An observer might not realize they're in a universe full of galaxies because most are so distant. This large-scale cosmic web continues to evolve. Over time, gravity will slowly pull filament galaxies toward the nodes, making clusters richer, while voids expand as matter drains out of them. However, the accelerating expansion of the universe, driven by dark energy, will counteract gravity on the larger scales, so the web might reach a sort of frozen configuration in the far future, where most structures don't grow much further because distant regions are receding too quickly to merge. Standing back, we can appreciate the cosmic web as the universe's grand design, the pattern underlying the distribution of galaxies. It's a bit poetic that galaxies, which themselves often look like webs of stars, spirals, are arranged in an actual web on a larger canvas. The phrase "connecting the dots" becomes literal. The galaxies outline the connections in this web. Now, an important component of that web and of galaxies' internal structure is something we mentioned earlier, but did not fully explore: dark matter. This is the unseen scaffolding that holds galaxies together and forms the framework of the cosmic web. It is the backbone of structure formation, yet it remains mysterious. We recall the evidence. Stars in the outer parts of spirals orbit unexpectedly fast. If visible matter were all there is, those outer stars should be moving slower, just as outer planets in the solar system orbit the sun more slowly, following Kepler's laws. Instead, galaxies' rotation curves flatten out. Stars far from the center orbit at roughly the same speed as those closer in. The logical conclusion is that there's much more mass spread out through the galaxy's halo than we can see, providing the extra gravity to keep those stars bound in fast orbits. Similarly, galaxies and clusters move as if there's far more mass in the cluster than the galaxies, and hot gas alone account for. Thus arose the concept of dark matter halos. Each galaxy is enveloped in a halo of dark matter, extending well beyond the visible starry disk or body. In the Milky Way, for example, our visible disk is 100,000 light-years across, but our dark matter halo may span 600,000 plus light-years. Most of the Milky Way's mass, 85%, is in this halo. We don't see it. We only feel it gravitationally. What is dark matter? We don't fully know. It could be a new type of particle, often theorized as WIMPs, weakly interacting massive particles, or something like axions. We have evidence it's not made of ordinary atoms. Observations of the primordial elemental abundances and the cosmic microwave background imply normal matter is only 5% of the cosmic energy budget, while dark matter is 27%. Dark matter doesn't clump into stars or planets. If it did, we'd see those objects gravitationally or via blocked starlight. Instead, it seems to form diffuse halos. One striking illustration of dark matter's reality is the Bullet Cluster. Two galaxy clusters collided. The fiery crash of their normal matter, hot gas, can be seen in X-rays, slowed and squeezed at the center of the collision. But the galaxies themselves, mostly empty space, passed through and, here's the key, gravitational lensing maps show the main mass concentrations went through largely unimpeded, now ahead of the visible gas. The interpretation, the dark matter of each cluster, being collisionless, sailed through with the galaxies, whereas the gas, normal matter, interacted and was left behind. This separation of mass via lensing and normal matter via X-ray is a direct sign that the bulk of the mass is not in the gas or galaxies, but in dark halos. In galaxy formation, dark matter collapsed first into a web of filaments and halos. Without it, the gas alone, affected by pressure and radiation, would not have aggregated into structures as early as it did. Dark matter provided deep gravitational wells to collect gas and seed galaxy formation. Galaxies formed at the centers of these halos. Even now, galaxies live at the bottom of their dark matter halos, like luminous ships at anchor in an invisible harbor. As galaxies merge, their dark halos merge too, creating ever larger halos. In clusters, the dark matter halo of the cluster holds the member galaxies together. In our local group, the combined dark matter halo of the group might eventually encompass both the Milky Way and Andromeda, and all satellites into one enveloping structure. Yet, despite making up most of the matter, dark matter is elusive. It doesn't emit light, so we cannot see galaxy halos directly. We detect them via rotation curves, via galaxy motions and clusters, via gravitational lensing, distant galaxy images distorted by foreground mass. We build detectors deep underground, hoping a stray dark matter particle might collide with an atomic nucleus and give a tiny signal. So far, no definitive detection, but the hunt continues. Living inside a galaxy's dark matter halo is imperceptible. It's like living at the bottom of a deep ocean of gravity, but one that is calm and transparent. We feel only the net effect. For example, our solar system's motion around the Milky Way is faster than it would be from visible matter alone, thanks to dark matter. Perhaps occasionally, a dark matter particle zips through us without a trace. They are thought to interact so weakly that trillions pass through your body each second with nary a hint. Dark matter doesn't collide with itself in the normal sense, so halos tend to be puffed out and roughly spherical. Non-collisional matter doesn't flatten into disks. This is why the luminous part of a spiral is flat, but the dark halo is spherical and much larger. In summary, dark matter is the silent, invisible partner in the cosmic dance. It forms the scaffold on which galaxies are built and the glue that holds them together. Without it, the elegant spirals might fly apart, and the cosmic web itself would be a flimsy network rather than the solid frame of the universe. Having this unseen mass everywhere gives the universe a hidden richness. When we gaze at a beautiful galaxy, we should remind ourselves that what is visible is only a small fraction, like the tip of an iceberg gleaming above water, with the bulk submerged. When we see galaxies cluster, we must imagine the great clouds of dark matter encompassing them, overlapping, merging, anchoring the cluster's gravity. We often call galaxies island universes, but even islands are connected beneath the ocean's surface by the shape of the ocean floor. And so galaxies are connected by the dark matter landscape. They ride the currents and settle into the valleys carved by this invisible mass. In the present day, dark matter continues to influence how galaxies move within groups and clusters, and how those structures evolve under cosmic expansion. So we have galaxies luminous and dark, the interplay of shining stars and unseen mass. This interplay is on display when galaxies collide. We move now from the serene picture of a single galaxy to the dramatic scene of galaxies interacting. Sometimes, galaxies do not remain isolated. Gravity draws them together, and they can collide and merge. When galaxies collide, it's a slow-motion dance lasting hundreds of millions of years. Their stars are so sparsely distributed that the chance of star-to-star collision is extremely low. Most stars just sail past each other. But the galaxy's structures, their disks, arms, and gaseous contents, distort and intermingle under gravity's pull. The result can be both destructive and creative. Destructive in that the original orderly forms, like spiral arms, can be stretched into tidal tails or completely scrambled. Creative in that the collision often compresses gas and sparks tremendous bursts of star formation, and eventually forms a new, often larger galaxy. Picture two spiral galaxies drawing near. As their halos begin to overlap, each feels the other's gravity. The nearer edges of their disks tug on each other. Tidal forces draw out long streams of stars and gas from each galaxy, throwing them into intergalactic space. These are tidal tails, graceful arcs that can extend tens of thousands of light years beyond the merging galaxies. One famous example, the antennae galaxies, NGC 4038-4039 in Corvus. They are two merging spirals that have flung out long tails resembling an insect's antennae. Within their overlapping region, a frenzy of star formation is occurring, gleaming blue and pink in Hubble images. Over the next few 100 million years, those two cores will likely coalesce into one remnant galaxy, perhaps an elliptical, and the tails may fall back or drift away. During a collision, the stars mostly act like collisionless particles. They change trajectories due to the altered gravitational field, but rarely hit each other. Gas, however, behaves differently. Gas clouds do collide, shock, and collapse. So galaxy collisions often trigger starbursts as gas is funneled and compressed. In the antennae, for instance, hundreds of young star clusters, some superstar clusters far more massive than any in the Milky Way, have formed due to the encounter. In another well-known pair, M81 and M82, the larger galaxy M81 pulled gas out of M82, inducing a massive starburst in M82, hence its bright red core and superwind. Collisions can also feed central black holes. Perhaps merging two disks drives gas to the center to light up a quasar, as likely happened in many quasars' histories. The shapes produced in collisions are diverse and often visually stunning. Aside from tidal tails, we see ring galaxies, like the Cartwheel Galaxy, where presumably a smaller galaxy punched through the center of a disk, sending outward a ripple of star formation that appears as a ring. Shell galaxies, ellipticals with faint concentric stellar shells, likely remnants of past mergers that settled in oscillating layers, and completely amorphous mergers where the entire system is a chaotic cloud of stars, eventually to relax into an elliptical. Galactic collisions also can fling stars entirely out of galaxies, creating intergalactic stars. In clusters, we find a diffuse light between galaxies, partly from stars stripped during close encounters or mergers. In our local group, our Milky Way's interactions with dwarfs have left streams of stars, such as the Sagittarius stream, orbiting independently. Each collision is a one-time, unrepeatable event, with unique outcomes depending on masses, speeds, angles, and gas content. But generally, two similar mass disk galaxies merging will produce a more spheroidal galaxy and cease most star formation, especially if the merger uses up or expels the gas. Many scientists think that's why giant ellipticals in clusters exist. They are essentially merger pileups of many former spirals and dwarfs. From the perspective of any beings within a galaxy during a merger, the night sky would change over millions of years. They might see a faint smudge of the approaching galaxy grow larger and more detailed. Perhaps new bright stars and nebulae would appear as star formation ignites. Over long times, the constellations would be disturbed as star positions shifted gravitationally. If they survived to the end of the merger, which any individual star likely would, since direct stellar collisions are rare, they might find themselves in a very different type of galaxy, perhaps lacking a clear disk or patterns, and their sky now filled with a diffuse glow rather than a crisp Milky Way band. Destruction breeds creation. The old forms of galaxies are destroyed, but new arrangements of stars and new stars themselves are born. Tidal tails created by one merger might later condense into dwarf galaxies, essentially giving birth to new smaller galaxies as byproducts of a big merger. In fact, some astronomers suspect that certain dwarf galaxies around giants could be tidal dwarf galaxies from past interactions rather than primordial objects. Over time, most galaxies will participate in at least minor mergers. Our Milky Way is currently cannibalizing some dwarfs as noted, and in the future will engage in a major merger with Andromeda. In about 4 billion years, Andromeda's disk will start to distort the Milky Ways, and by 5 to 7 billion years, they will likely coalesce into a single elliptical-like system, nicknamed Milkomeda. This merged galaxy may then eventually gather the other local group members. Farther down the line, billions of years later, it might even fall into the Virgo cluster, though cosmic expansion might prevent that. Nothing is truly static. Collisions highlight another feature. Galaxies contain a lot of empty space relative to their size. If two spirals were shrunk to the size of two frisbees and thrown at each other, one might expect a smash. But in space, even when their disks overlap, stars mostly miss each other because of scale. The frisbees in this analogy are loaded with grain of sand stars inches apart. Two thrown frisbees would result in many sand grains colliding. But in galaxies, stars are like grains, perhaps miles apart on those frisbees. Not a perfect analogy, but it gives a sense of the sparseness. Ultimately, colliding galaxies tend toward equilibrium, Eventually, the gravitational chaos settles into a new, stable shape, often an elliptical. The wild star formation consumes gas and then peters out. The stellar orbits randomize and the system becomes dynamically relaxed. What was two lively spirals becomes one big, perhaps complacent, elliptical. Destruction creates beauty. The antennae-like tails, the rings, the burst of nebulae, all transient loveliness in the cosmic theatre. Eventually that fades, and a more subdued form remains, carrying in its diffuse light the mixed heritage of its progenitors. We see many ellipticals with faint tidal features or multiple nuclei or other signs that they formed from mergers, ghosts of their past lives etched in starlight. Thus, galaxies not only live, they can also reproduce in a sense, two become one, spawning perhaps smaller offshoots in the process, like tidal dwarfs. The number of galaxies can change with time, in regions like clusters. Initially, many moderate galaxies merged into fewer large ones, galactic cannibalism. In our local group, the number of substantial galaxies will reduce from two major, Milky Way, Andromeda, to one. But the combined light and mass remain roughly the same, minus whatever is ejected into intergalactic space. Having considered this tumult of collisions and growth, let us return to a familiar vantage. Our own galaxy, the Milky Way, which has thus far led a somewhat quieter life, allowing life to arise here. We have seen how galaxies in general work. Now we focus on the specific characteristics of the one we call home. The Milky Way is a barred spiral galaxy with a disk over 100,000 light-years in diameter. It has a central bulge of stars, about 10,000 light-years thick, and a bar of stars about 25,000 light-years long crossing the bulge. From the ends of this bar emanate the spiral arms. At least two major arms, Scutum Centaurus and Perseus, and several smaller segments or spurs, like the Orion arm where our Sun resides. Our galaxy's total stellar mass is on the order of 100 billion suns. It's accompanied by a retinue of over 50 satellite galaxies, mostly dwarfs, and is itself part of the local group with Andromeda and others. We experience the Milky Way from within. On a clear night in a dark location, we see it as a milky band arching across the sky. That is our edge-on view of the dense galactic disk. Through telescopes, this band breaks into countless faint stars and dark dust lanes. Toward the constellation, Sagittarius lies the galactic center, about 27,000 light-years away, behind thick dust clouds that hide the nucleus in visible light. In that direction, the Milky Way band is widest and brightest because we are looking toward the packed central bulge and along several spiral arms overlapping. At the center, beyond visual reach, sits the Milky Way's supermassive black hole, Sagittarius A. We have mapped stars orbiting extremely fast there, up to a few thousand km, indicating a mass of 4 million suns in a volume no larger than our solar system, hence a black hole. Currently, SGR-A is quiet. It's not actively accreting much gas, so it's effectively dark. If it were feeding, we'd detect strong radiation from that region, X-rays, etc. As mentioned, evidence of past activity, the Fermi bubbles, suggests it's had active episodes. Surrounding the nucleus is the bulge, a roughly spheroidal swarm of older stars, many red giants among them. The bulge has a higher proportion of old metal-rich stars, and likely also contains the bar structure. The bar is basically a stretched bulge. Our vantage point, offset from the center, means we see the bulge as a widening of the Milky Way's central glow. The disk of the Milky Way is the dominant feature. It is fairly thin, about 1,000 light-years thick in the star-forming regions, thicker in older stars. It contains most of the gas, in forms ranging from hot ionized regions to cold molecular clouds and dust. Our Sun orbits within this disk, currently about 25 pc, 80 light-years, above the midplane. We bob up and down through the plane as we orbit. The solar system completes one orbit around the center every 240 million years, sometimes called a galactic year. We've likely done about 20 orbits since the Sun's formation, meaning the Sun has been in various parts of the Milky Way's arms and spaces between arms over time. Our galaxy's spiral structure has been discerned by carefully mapping concentrations of gas via radio observations of hydrogen and carbon monoxide and young star clusters. We know that it has a barred center from infrared surveys like COBE and Spitzer that penetrate dust. The major arms are the Perseus arm, outside our orbit, and the Scutum Centaurus arm, inside our orbit, wrapping around the galaxy. The Sun lies in a smaller spur called the Orion Cygnus arm, or local arm. This local spur connects the major arms and contains the Orion Nebula, the Carina Nebula, and other nearby star-forming regions. Our galaxy is currently forming stars at a moderate clip, a few M per year, mainly in the spiral arms. Notable star formation complexes include those in Carina, Scutum, Sagittarius, all toward the inner galaxy, and the Perseus arm, farther out. We also have ongoing star formation in the molecular ring about 4 kpc, 13,000 Li, from the center, which might be related to the bar's dynamics funneling gas there. The Milky Way's halo is a roughly spherical zone surrounding the disk and bulge. In this halo are the oldest known stars of our galaxy, some nearly as old as the universe, found in globular clusters and as solitary halo stars passing through. We have observed about 150–160 globular clusters orbiting the Milky Way. These clusters are dense, gravitationally bound spheres of ancient stars, typically 12 billion years old or more. They reside mostly in the halo, on random elliptical orbits tilted at various angles to the disk. Harlow Shapley in the 1910s used the distribution of globular clusters. They form a roughly spherical cloud centered on the galactic center to infer the Sun's offset position and the size of the Milky Way, one of the first steps in understanding our galaxy's true scale. The halo also contains the dark matter halo mass. The stellar halo, visible stars, is tiny compared to the dark halo, but it's our tracer of the halo's extent. Many halo stars and globulars have very low metallicity, few heavy elements, indicating they formed when the galaxy, or its precursor fragments, was very young and mostly unpolluted by supernovae. Some might even predate the Milky Way, having formed in smaller progenitor galaxies that later merged into the Milky Way. The Milky Way sits in a neighborhood with dozens of other galaxies, the local group. Dominating our local group are the Milky Way and the Andromeda Galaxy, M31. Andromeda, slightly more massive and about 2.5 million light-years away, is a spiral galaxy quite similar in structure to our own, barred as well, with a vast swarm of satellites. The third largest member is the Triangulum Galaxy, M33, a smaller spiral, maybe 1/5 the mass of Andromeda, which might be a satellite of M31 or an independent member. Beyond these 3 spirals, the rest of the local group is composed of dwarf galaxies. Most of these are satellites of either the Milky Way or Andromeda, and a few lie in between. The Milky Way's notable satellites include the large and small Magellanic Clouds, 2 irregular dwarf galaxies visible prominently from the southern hemisphere. They contain active star-forming regions, like the Tarantula Nebula in the LMC, the most luminous star-forming region in the local group, and are interacting with our Milky Way. A stream of gas, the Magellanic Stream, stretches from them, drawn out by tidal forces. The LMC and SMC orbit the Milky Way at distances of 50 to 60 kpc, 160,000, 200,000 Li. Over the next few billion years, they may either merge with our galaxy or possibly be stripped apart. Other Milky Way satellites include dwarf spheroidal galaxies such as Sagittarius, Draco, Ursa Minor, Carina, Sextans, Sculptor, Fornax, and many discovered more recently, like Tucana 2, Reticulum 2, etc., found in data from surveys such as SDSS and DES. These are generally tiny, faint galaxies. Some have only a few million stars, and they often appear as barely detectable smudges of light in telescopes. They have little to no gas and are supported more by random motions of stars, not rotation, analogous to miniature ellipticals. They tend to reside within a few 100,000 light-years of the Milky Way, and some, like Sagittarius dwarf, are actually in the process of being tidally disrupted by it. Indeed, the Sagittarius dwarf, discovered in 1994, is wrapping around the Milky Way in a stream of stars, evidence caught in stellar surveys as an overdensity of certain tracer stars. Andromeda likewise has its cohort of dwarfs, like M32 and M110, two dwarf ellipticals right next to its disk, visible even in early photos by Messier, and many dwarfs discovered around it, such as Andromeda 1-2, etc., and the recent surprise of a thin plane of satellite galaxies seemingly aligned around M31. Triangulum, M33, is smaller and has only a couple of tiny companions known. The local group as a whole is about 3 million parsecs, 10 million light-years, across, and is gravitationally bound. The Milky Way and Andromeda are approaching each other. 110 km/s inward motion on top of some transverse motion. The group itself is moving toward the Virgo cluster, but likely will not reach it due to cosmic expansion. The local group's center of mass lies somewhere between the Milky Way and Andromeda. These two giants orbit that center and each other slowly. This little family of galaxies drifts together in space. Inside it, galaxies can affect each other. Our Milky Way is clearly affecting and consuming some of its dwarfs. Andromeda has likely swallowed some of its own. Its halo contains many streams indicative of past mergers. Eventually, as noted, the two big ones will merge. Effectively, the local group will condense into one galaxy containing most of the stars of the current group. The local group sits at the edge of the Virgo supercluster. Just beyond our group, about 15 million light-years away, lie small groups like the M81 group, around the spiral M81 in Ursa Major, and the Centaurus A M83 group, around Centaurus A, a peculiar elliptical, and M83, a spiral. Further out, how 50 to 60 million Li, is the Virgo cluster itself, a massive cluster of 2,000 galaxies. Our local group is being gently tugged toward Virgo, the Great Attractor region, which also includes the Centaurus cluster, Norma cluster, etc. But we are not part of Virgo. Rather, the local group is like a little outlying suburb of that enormous cluster complex. The environment of the local group, relatively isolated in a cosmic filament, has allowed the Milky Way and Andromeda to retain their gas and spiral forms longer than they might have in a dense cluster environment. It's a quieter corner of the universe. Now, not all galaxies in the cosmos are large like the Milky Way or Andromeda. In fact, by number, dwarf galaxies dominate. These are galaxies with much smaller masses and luminosities, often just a few million to a few 100 million stars instead of billions. Some dwarfs are irregular, like the Magellanic Clouds. Others are spheroidal or elliptical. Dwarfs are the building blocks that, assembled together, formed bigger galaxies. Many dwarfs also persist as separate entities, especially around bigger galaxies as satellites, or in isolation in voids. Dwarf galaxies are intriguing. Because of their low gravity, they're susceptible to having gas stripped or blown out. Many dwarf spheroidals around the Milky Way have no gas at all. Likely, the Milky Way's tides or radiation long ago removed it, or internal supernovae winds expelled it. These dwarfs consist mostly of old stars and are very faint. They are also extremely dark matter dominated. For example, the Draco dwarf contains only a few million solar masses of stars, but perhaps tens of millions of solar masses of dark matter. Its stars move as if a lot of unseen mass is present. making it effectively a lump of dark matter with a frosting of stars. This makes dwarfs excellent test beds for dark matter theories on small scales. Some dwarfs are more like surviving siblings of big galaxies, having converted only a small portion of their gas into stars and hanging onto their gas reservoirs for a long time. The Magellanic Clouds, for instance, still have plenty of gas and active star formation. The LMC even has its own satellites, a mini-system. In the early universe, many dwarfs probably merged into larger systems, but those that didn't can be seen as fossils of that time. We might liken dwarfs to cosmic plankton, tiny, numerous, easily influenced by currents, tidal forces from larger galaxies, yet absolutely essential in the food chain of cosmic structure. Without dwarf mergers, many larger galaxies would not have grown so massive. Without dwarf galaxies as satellites, big galaxies wouldn't have some of their halo stars, captured from dwarfs, or their extended globular clusters. Some globulars could be the nuclei of dwarfs that were consumed. The space between galaxy clusters is filled with isolated dwarf galaxies too, some in the process of falling into groups clusters for the first time. These tend to be gas-rich because nothing removed their gas yet, and are forming stars slowly. Over time, they might either form a few more stars and remain small, or eventually fall into a cluster and get stripped to become an ultra-diffuse cluster member. One fascinating aspect: dwarfs can have difficulty hanging on to not just gas, but also metals. When a star in a tiny galaxy explodes as a supernova, the blast can accelerate gas past the dwarf's escape velocity, blowing heavy elements out into intergalactic space. So many dwarf galaxies have much lower metallicity than larger ones of similar age. They lost more of the metals their stars produced. In this way, dwarfs pollute the intergalactic medium, enriching the cosmic environment with elements that later might be incorporated into other galaxies or proto-galaxies. Thus, dwarfs, though small, play a role in cosmic chemical evolution disproportionate to their size. In our local group, the ongoing accretion of dwarfs by the Milky Way and Andromeda is an example of the galactic cannibalism that likely happened frequently in the past. The halos of large galaxies are essentially graveyards of smaller ones, strewn with their tidally torn debris. We see these as stellar streams in our halo, like the Sagittarius stream, GD1, PAL5 stream, etc. Andromeda too is laced with streams. Each is the remains of a dwarf galaxy or globular cluster consumed and assimilated. Over time, those streams will phase mix into the halo, becoming indistinguishable smears of stars, adding to the smooth halo light. While many dwarfs live as satellites, some are relatively isolated. For instance, the tiny galaxy Wolf-Lundmark Melotte, WLM, on the outskirts of the local group a 3 million Li away, is a dwarf irregular that has led a solitary life, slowly forming stars, barely interacting with bigger neighbors. It gives us a glimpse of how a very small galaxy evolves on its own. In sum, dwarf galaxies are crucial pieces of the cosmic puzzle. They were the seeds of larger galaxies and remain the most common galaxy type by number. Often overlooked due to their faintness, they carry important clues about the early universe, the low mass end of galaxy formation, and the nature of dark matter through their extreme mass-to-light ratios. We, within the Milky Way, are currently treating our dwarf neighbors in a mixed way. Some we nurture. The Magellanic Clouds are being drawn in and likely eventually will mix with us. But for now, they're triggered to form stars maybe by our tidal influence. Some we have torn apart, Sagittarius, and others orbit peacefully for now, Fornax dwarf, etc., which still have some old stars and even globular clusters of their own. In a few billion years, if any distant future astronomers compile a census, they might find that what was once dozens of dwarfs became just stellar streams in an enlarged Milky Way halo. Now, galaxies not only consume matter and form stars, they also breathe, in a sense. Massive stars and active nuclei can drive galactic winds, outflows of gas that extend far beyond a galaxy's main body. Through these winds, galaxies can expel some of their content into intergalactic space, influencing their surroundings and regulating their own growth. In a star-forming galaxy, especially one experiencing a starburst, the combined effect of many supernovae and stellar winds can create a superwind. We see a dramatic example in the Cigar Galaxy, M82, which we encountered as a starburst triggered by interaction. M82 shows twin reddish plumes of gas billowing out perpendicular to its disk. This is a galactic wind. What's happening is that thousands of supernovae from the central starburst have heated and propelled gas outward. This gas, a mix of hot plasma and cooler entrained material, is leaving the galaxy's gravitational grasp. Some of it might fall back later, but much may escape into intergalactic space. Along with gas, metals, carbon, oxygen, etc., are carried out, meaning the galaxy enriches its environment. Galactic winds are crucial in galaxy evolution. They can remove gas that would otherwise form more stars, effectively putting the brakes on star formation, especially in smaller galaxies where the gravity is weaker. It's easier for a wind to evacuate a dwarf galaxy than a giant one. This is one reason dwarfs often have low star formation rates or shut off early. They lost their gas to winds. Even in large galaxies, winds, often aided by an active black hole's energy output, can clear out the central regions and halt star formation there, leading to the kind of gas-free bulges we observe. Winds also disperse the ashes of stellar furnaces, the heavy elements. The intergalactic medium in galaxy clusters is observed to be enriched with iron and other metals, likely supplied by winds from member galaxies' past starbursts and outflows from active nuclei. In the early universe, before clusters existed, proto-galaxies likely blew metals into intergalactic space, seeding the raw primordial gas with heavier elements. So galactic winds are like the breath of galaxies that pollinates the cosmos. Another aspect is that winds can interact with a galaxy's surroundings. In a cluster environment, one galaxy's wind might slam into the intracluster medium, producing shocks. We sometimes observe X-ray or radio features in clusters that correspond to past winds or jets. In the cosmic web filaments, winds from galaxies can spread metals along the filament, enriching gas that might later fall into other galaxies downstream. Our Milky Way has modest outflow activity now, but evidence suggests that it too has or had a galactic wind. Aside from the Fermi bubbles produced by past AGN activity, there's also a structure called the galactic chimney, or the northern chimney, a region above the disk where hot gas from widespread star formation in the past may have vented out of the disk. The halo of our galaxy contains traces of elements that likely came from past outflows. When enough gas is expelled, it can eventually cool and rain back down, a process called a galactic fountain. In some spirals, localized starbursts blow gas out, which later falls back in a gentle drizzle elsewhere, redistributing metals across the disk. The Milky Way's halo gas, detected in UV absorption lines, might partly be fuel that is slowly cooling and returning, or fresh infall from outside, probably a mix of both. All this breathing, outflow and inflow is part of the self-regulation of galaxies. Too much star formation? Winds blow out gas, slowing things. Later, if the galaxy is quiet, it might accrete more gas again from its surroundings, or the expelled gas might cool and fall back, allowing a new cycle of star formation. This feedback loop helps explain why galaxies don't use all their gas at once in a single burst, except perhaps extreme starbursts, which essentially do and then become dormant. In the big picture, galactic winds are one of the mechanisms linking the small scale of stars to the large scale of galaxy groups. They enable material and energy exchange between a galaxy and the intergalactic medium. Through winds, galaxies essentially communicate with the universe, sending out signals in the form of enriched gas and receiving, in turn, sometimes pristine gas later. So we have painted a portrait of a galaxy's internal life. Stars forming and dying, black holes growing and regulating, gas being cycled and sometimes expelled. Galaxies are not closed ecosystems. They interact with their environment gravitationally and through these winds and outflows. Let us now step back to a more distant time, when galaxies and black holes were in their most exuberant phases. In the young universe, quasars and active galactic nuclei were far more common. A quasar, short for quasi-stellar object, is the extremely luminous core of an active galaxy, powered by rapid accretion onto a supermassive black hole. During the peak quasar epoch, roughly 10 to 12 billion years ago, many forming galaxies shone as intensely bright quasars, visible clear across the universe. Quasars are among the brightest objects in existence. Some radiate the power of trillions of suns from a region no larger than our solar system. The nearest quasar to us, for instance, is dozens of times farther than Andromeda, yet can be seen in modest telescopes as a faint star-like point. And more distant quasars, whose light began traveling to us when the universe was only a billion years old, are detectable because of that immense luminosity. These beacons signaled that massive black holes were rapidly devouring matter in early galaxies. Often, quasars are associated with disturbed, merging galaxies, hinting that a collision funneled gas into the nucleus. The incredible output of a quasar is multi-wavelength, visible light, ultraviolet, X-rays, infrared. The accretion disk emits a broad spectrum. Quasars also often produce jets that emit radio waves. Some of the first quasars were discovered via radio surveys. Observationally, a quasar appears star-like, hence quasi-stellar, because at tens of billions of light-years, the host galaxy's extended light is too faint to see. Only the brilliant core registers. It was through spectroscopy that astronomers in the 1960s realized these star-like objects had enormous redshifts, implying they were incredibly distant and thus incredibly luminous to be visible at all. That realization expanded our understanding of both galaxies and black holes, revealing that some galaxies in the distant past went through a quasar phase. As the universe aged, quasars became rarer. Why? Likely because the fuel supply at galactic centers became less abundant once major mergers became less frequent and most central black holes had reached a satiation point. The quasars we do see nearby are relatively less powerful AGN, or are cases of a late accretion event. For instance, a galaxy might reignite its nucleus by swallowing a gas-rich dwarf. Active galaxies come in various forms: quasars and Seyfert galaxies, active nuclei in spiral galaxies, radio galaxies, ellipticals with huge jets and lobes of radio emission, blazars, AGNs whose jets point directly at us, making them appear especially variable and bright in high-energy output. All are manifestations of the same engine, accretion onto a supermassive black hole. The differences are often in orientation and scale. A unified model suggests that a quasar and a radio galaxy could be the same type of object viewed from different angles, with or without seeing the jet, etc. These active phases likely have finite duration, maybe a few million to tens of millions of years for a quasar-level episode. Some galaxies may have undergone multiple episodes if conditions allowed, e.g. periodic infall of fresh gas. In fact, our Milky Way's center might have flickered as a weak quasar for short spurts when it had access to enough gas. The evidence of past activity hints at that. What do quasars mean for galaxy evolution? As discussed, they are an extreme form of AGN feedback. A powerful quasar can blow out the bulk of a galaxy's gas, effectively truncating star formation. So quasars likely mark the end of growth spurt for their host galaxies, a sign that the galaxy has accumulated a large black hole and is now clearing itself out. It's like a candle flaring brilliantly just before it exhausts its fuel. From a cosmological standpoint, quasars are useful beacons for studying the early universe. Their light, traveling billions of years, carries information about the intergalactic medium it passed through. We see absorption lines from intervening gas clouds in quasar spectra, which has told us about the distribution of matter in the young universe, the rise of cosmic metals, and the epoch of rionization, the tail end of the Dark Ages, when early light sources rionized hydrogen. The farthest known quasars, with redshifts around 7.5, universe age, 700 million years, challenge our understanding. They have black holes, 1 billion solar masses already, meaning black holes and galaxies can grow very quickly in the right circumstances, probably via rapid, direct collapse of gas and early mergers. As we contemplate other galaxies, especially those outside our immediate cosmic neighborhood, we might see many that no longer have quasars, but carry evidence that they once did. Perhaps an oddly low gas content, or an overmassive black hole relative to their current size. The imprint of that active past can linger. We, collectively as a cosmic memory, look back at the epoch of quasars as a time when the universe itself was in a tumultuous youth. Galaxies were colliding frequently, star formation rates were high, and central black holes were feasting. It was a mysterious, energetic, almost violent phase, yet also one that seeded the calmer cosmos we inhabit now. Quasars, in their brilliance, helped bring an end to the era of universal star frenzy and paved the way for the mature galaxies of today. Now we shift focus to how we know all this, how we observe galaxies across light and time. We humans, tiny creatures within one galaxy, have managed to build instruments that extend our senses to the edges of the cosmos. Through them, we piece together the life stories of galaxies. When we look at a galaxy, we are also looking into the past. Light takes time to travel. When you see Andromeda tonight, you view it as it was, 2.5 million years ago, when early hominins on Earth might have just begun using stone tools. The farthest galaxies we observe appear to us as they were mere hundreds of millions of years after the Big Bang. Thus, astronomy is like time travel by vision. By observing more and more distant galaxies, we essentially watch the cosmic movie in reverse. Nearby galaxies show the present frame, far galaxies show earlier frames. Our primary tools are telescopes that capture different wavelengths of light because galaxies emit or absorb across the spectrum. With optical telescopes like the Hubble Space Telescope or large ground-based observatories, we see the stars and star clusters, the shapes of galaxies, and sites of active star formation outlined in high emission. Infrared telescopes, like the Spitzer Space Telescope and now the James Webb Space Telescope, can see through dust to reveal stars and structures hidden in dusty regions, such as the Milky Way's center or star-forming molecular clouds. Infrared also picks up the glow of cooler, older stars that dominate galaxies like ellipticals, and it can detect redshifted light from very distant galaxies that has been stretched into infrared wavelengths by the expansion of the universe. Ultraviolet telescopes, like galaxies, highlight the most massive young stars and thus pinpoint where star formation is happening in a galaxy. X-ray observatories, Chandra, XMM Newton, see the high-energy processes, accreting black holes in AGN, shining in X-rays, and hot gas in clusters or galaxies. Radio telescopes map cold gas, notably the 21 centimeter line of neutral hydrogen, and also synchrotron emission from relativistic electrons in magnetic fields, tracing things like jets and supernova remnants. Each wavelength adds a layer to our understanding. For example, optical images of a spiral might show a pretty pattern of arms and some dark dust lanes, but a radio map of the same galaxy might reveal huge spiral extensions of hydrogen gas beyond the visible disk, perhaps warps or streams connecting to neighbors. Ultraviolet might show that the outer disk has clumps of young stars beyond where optical light seemingly ends. Infrared might unveil a barred structure in the core invisible in optical due to dust. It's like examining an organism under different types of light to see different components, bones with X-rays, heat with infrared, etc. One of the most powerful techniques in observing galaxies has been spectroscopy.
By dispersing a galaxy's light through a prism or grating, we see spectral lines, signatures of elements in stars or gas. From these, we measure velocities via Doppler shifts. We can thus gauge how fast parts of a galaxy rotate, leading to those rotation curves for dark matter studies. We can measure how fast galaxies themselves move relative to us, the redshift, which in the context of universal expansion tells us their distance. Spectra also reveal chemical abundances, e.g., the strength of certain lines indicates how much heavy elements the gas has. Thus we know, for instance, that dwarf galaxies typically have low metallicities compared to large galaxies. Combining imaging and spectroscopy across wavelengths, we have developed a fairly complete medical chart for galaxies. Their masses, their compositions, their star formation rates, their temperatures, color indices or spectra, their environments, and so forth. With that, we infer their histories. We owe much to telescopes like Hubble for visualizing the distant universe. The Hubble Deep Field in 1995, for example, was a long exposure on a tiny patch of apparently empty sky. The resulting image revealed thousands of faraway galaxies of all shapes and colors. A cosmic scrapbook of galaxy evolution. We saw tiny blue galaxies, probably distant irregulars or spirals in their star-forming prime. Larger reddish galaxies, perhaps already formed ellipticals in the background. Odd interacting pairs, chain-like clumpy galaxies, etc. This one picture revolutionized our appreciation of how many galaxies are out there, an estimated hundreds of billions in the observable universe, and gave a snapshot of galaxies billions of years ago. Recently, the James Webb Space Telescope, with its infrared vision, has begun to see even further back, identifying candidate galaxies at redshifts above 10, within 500 million years of the Big Bang. These are extremely faint, and often just red smudges or dots even to Webb. But their existence is exciting. They might be among the first generations of larger structures. Some have unusually high brightness or masses, prompting astronomers to recheck how quickly galaxies could have grown. Webb's early data hints that some galaxies got big surprisingly fast, which could challenge or refine our models of early star formation and dark matter collapse. Gravitational lensing has been another boon. Massive clusters can magnify and stretch the images of background galaxies behind them. With lensing, we have observed galaxies that would normally be too faint or small. For example, the galaxy dubbed Earendel, after a Tolkienian name meaning morning star, was detected by Webb. It's a highly magnified image of what might be a single star or star cluster in a galaxy 12.9 billion years in the past, magnified by a factor of thousands by a foreground cluster's lensing. Likewise, Hubble found the most distant galaxy known, GNZ 11 at redshift HUT 11, via deep field imaging and spectroscopic confirmation, capturing it thanks to its relative brightness, possibly enhanced by lensing or an inherent starburst. The observable universe is limited, but within that horizon, our instruments have reached remarkably far. The edge of what we can see is basically defined by the faint afterglow of the Big Bang, the cosmic microwave background, at redshift L1100. We cannot see galaxies past a certain redshift because there were none before a certain time, and because beyond a certain point, space expansion carries them away, such that their light hasn't reached us yet. What does the edge of visibility look like? As discussed, the farthest confirmed galaxies and quasars are around redshift 7 to 10, the universe 500 million to 700 million years old. Beyond that, we expect only proto-galactic fragments and the first light of stars reionizing the universe. There's a race on. Can JWST or future extremely large telescopes detect galaxies at redshift 15, 20? Possibly not bright galaxies, but maybe hints of star clusters or supernovae in that era via some serendipitous events. With each improvement in technology, larger telescopes, better detectors, new wavelength windows opened, we peel another layer of the universe's story. In the coming decades,
New observatories like the Rubin Observatory for optical surveys, the Roman Space Telescope, infrared wide field, great for finding early galaxies via lensing surveys, ELTs, extremely large telescopes, 30-40 mils class on the ground, and maybe one day missions like LUVOIR or HABEX could allow us to map out even more of the universe's galaxies and even take spectra of extremely distant faint smudges to definitively gauge their ages and compositions. In doing this, we must preserve humility. We see snapshots, and from snapshots, we reconstruct narratives. Sometimes a galaxy can trick us. Two galaxies superposed can look like one odd one, or a transient event can make a galaxy seem more luminous. But overall, the consistency of evidence gives us confidence in the broad strokes of cosmic history we've outlined. Our viewpoint from inside the Milky Way is both a blessing and a curse. Curse in that dust and our position make mapping our own galaxy challenging. We did not even know the Milky Way's spiral structure well until the mid-20th century. But blessing in that, we have a ringside seat to a galaxy's internal details. We can study individual stars in galaxies, at least our own and near neighbors, which is impossible in far galaxies. Thus, we use the Milky Way as a template to understand certain fine-grained physics and external galaxies to place the Milky Way in context. We see that our galaxy is just one of a vast population, typical in some ways, perhaps a bit above average in mass, but certainly not unique except to us. Using light as our messenger and time machine, we have observed galaxies through 13+ billion years of cosmic evolution. We've catalogued their variety and, in doing so, discovered our own origins. Every image of a distant galaxy is also an image of what our own might have looked like long before the Earth existed. In that sense, observing galaxies is a form of introspection for the universe. It is the cosmos looking back at itself through us, examining different chapters of its autobiography. As we push the boundaries of observation, we approach the edge of the observable universe. This is the maximum distance from which light has had time to reach us since the Big Bang. It's about 46 billion light years away, not 13.8 billion, because as light traveled, the universe expanded. At that horizon, galaxies, or protogalaxies, are seen at the very dawn of cosmic time, if at all. Beyond it, light from any object is still en route and won't arrive until the future, or, if beyond the event horizon set by accelerated expansion, perhaps never. Already, at redshifts around 1011, we observe galaxies that are basically at the limit of current capabilities. They appear as tiny red dots. Their light has been traveling 13.3 billion years. Those galaxies likely are small and just forming their first batches of stars. They might eventually merge to become larger galaxies later. We are seeing them in embryonic form. At slightly higher redshifts, 15 or 20, any stars or clusters might be even younger. Possibly we're talking about the first sizable star clusters forming, each perhaps too faint individually for us to see without extreme lensing help. Eventually, as we near redshift 1000, we hit the surface of last scattering. Before that, the universe was opaque plasma, so no direct photons can come to us from earlier times, except neutrinos or gravitational waves potentially, but that's another story. So we have a cosmic photo album that starts around the birth of visible galaxies and continues to the present. What lies beyond our observable universe? Likely more of the same cosmic web, galaxies and voids extending indefinitely, or at least to some huge extent. But that region is forever inaccessible to us due to the finite speed of light and cosmic expansion. In a sense, those unobservable galaxies are like ghosts, real, but we will never see their light. It's strange to think that the universe could be vastly larger than what we can observe, containing countless galaxies forever beyond our horizon. However, within our horizon, we have what appears to be a fair sample of the universe's contents. The distribution of galaxies and their properties seem uniform on large scales. The cosmological principle, no special spot.
so likely the observable portion is representative of the whole. We can, with some confidence, generalize that galaxies exist everywhere in similar ways. As time marches on, the edge of our observable universe moves outward. We catch light from slightly more distant regions. But concurrently, due to accelerated expansion, distant galaxies are moving away faster and faster. Eventually, there's a limit. Distant galaxies' light gets redshifted into oblivion or never reaches us if space expands too swiftly. In fact, billions of years in the future, an observer in our Milky Way, or its merged descendant, will see fewer and fewer external galaxies. Far-off galaxies will slip beyond detectability. Closer ones will eventually follow. Trillions of years hence, perhaps only the local group's merged remnant will be visible to its inhabitants. All other galaxies' light will have stretched beyond recognition or dropped below detectable levels. The universe will seem to them an empty, dark void with one galaxy, a very different cosmic vista than the rich one we enjoy now. But that far destiny is far beyond our concern. At present, we stand at a time when the universe's story is richly accessible. We can look back almost to the beginning and see evidence of those earliest chapters. We see the whole sweep, from primordial galaxies just lighting up, through the turbulent adolescent universe of quasars and starbursts, to the settled modern universe of grand spirals and ellipticals, and even hints of the quiet senescence to come in some galaxies. Galaxies also change internally over time. They age. We have already touched on this. Star formation slows as gas runs out. Stellar populations shift toward older, redder stars. An active blue spiral can become a passive red lenticular or elliptical. The universe's population of galaxies is undergoing an overall aging. The cosmic star formation rate today is about an order of magnitude lower than it was 10 billion years ago. Many galaxies that once were lively are now quiescent. We observe this directly. In clusters at moderate distances, a few billion years ago, we see more spirals and irregulars than in nearby clusters, where most galaxies are ellipticals/lenticulars. In the field, we see that the fraction of star-forming galaxies was higher in the past. The transformation mechanisms, mergers, environment, internal exhaustion, have gradually quenched many galaxies. An aged galaxy, like a massive elliptical in Virgo, is essentially a memorial to its youthful past. Its light is now mostly from low-mass, long-lived stars, orange K-giants, red dwarfs, etc. The O and B stars that once made it blue are gone. They lived short lives long ago. Without new stars, the galaxy has slowly reddened. In a sense, galaxies have colors akin to leaves. A bright star-forming galaxy is like a green leaf full of chlorophyll, young, vigorous, while a quenched galaxy is like an autumn leaf that's turned red-brown. The green, blue light of young stars is gone, leaving the oranges and reds of the older population. Some galaxies can be rejuvenated if they get new gas. For instance, a previously quenched lenticular might accrete gas from a companion or the intergalactic medium and reignite some star formation. But generally, once a galaxy becomes a large elliptical, it doesn't return to a spiral. Too much structural change and gas loss has occurred. Rejuvenation usually happens in smaller doses, like a very low level of star formation on top of an old population, often seen in S0 galaxies that have a few patches of star formation from some residual or acquired gas. As eons pass, galaxies will continue to fade. One can extrapolate, in about 100 billion years, with no major external influences, the Milky Way, if it hadn't merged with Andromeda, hypothetically, would use up much of its gas and form mostly red dwarfs. The bright blue stars it has now will be long gone. Even the Sun will be a white dwarf by then. The galaxy's luminosity would decline. Low-mass stars can burn for extremely long times, trillions of years for the smallest red dwarfs, so the galaxy would never go completely dark in the foreseeable future. but it would become very faint and mainly infrared, since red dwarfs emit in red IR. Planets and remnants might still orbit quietly, but the grand star formation nebulae and massive clusters would be distant memories. A truly old galaxy would be a sparse collection of slow-burning embers. Imagine, trillions of years hence, a lone red dwarf civilization looking out at a night sky where maybe only red and orange stars speckle the heavens and no Milky Way band, because the bright contributors to it have died out. That's a far extrapolation, but it is where aging leads. However, interactions can reset the clock for some galaxies. The Milky Way, for example, will merge with Andromeda and likely spark a wave of new star formation as gas clouds slam together, thus temporarily making a new blue generation of stars before settling down to red retirement. So galaxies can have multiple epochs of youth in a way, e.g., after a quiet period, a merger can make them briefly young again in terms of star content. These cycles complicate a straightforward age narrative, but overall, as the universe's expansion dilutes fresh infall and as available unmerged galaxies dwindle, rejuvenations will become rarer. Eventually, most star formation will wind down everywhere. In the present, we still see a mixture. Some galaxies are in their vigorous star-forming phase, especially many smaller ones and some big ones like grand design spirals. Others have already quieted down. This mix is part of the so-called galaxy bimodality. The cosmic population tends to split into blue star-forming galaxies and red quiescent galaxies, with fewer in between. This tells us that the transition, blue to red, can be relatively rapid on cosmic timescales, a few 100 million years perhaps to quench a galaxy via a merger or other means. Thus, a galaxy might spend a few billion years actively forming stars, then, after a quenching event, fade to red and spend tens of billions of years in that state. While galaxies change, the universe around them changes too. Expansion continues, and the balance between gravity and expansion determines whether structures grow or not. Currently, we are in a phase where expansion wins on the largest scales, so the cosmic web is sort of frozen beyond supercluster scales, and within those scales, gravity still slowly merges galaxies within bound groups/clusters. In the far future, each bound group or cluster will merge into one huge galaxy. So ironically, while individual galaxies fade, the average galaxy's mass may actually increase due to mergers, but those will be the last major ones. Now, shifting from physical changes to a more speculative realm, consider the possibility of life in other galaxies. As we look at the myriad galaxies, we cannot help but wonder, is there life out there? And if so, how abundant is it? We know life arose in one galaxy, our own, at least on one planet. Given the vast number of galaxies and stars, it seems statistically inevitable that many galaxies harbor life-bearing worlds. Each galaxy contains billions of stars and likely billions of planets. Even if only a small fraction of stars have habitable zone planets, the sheer numbers mean potentially millions of such planets per galaxy. And with billions of galaxies, well, the number of possible abodes for life becomes astronomical indeed. We, beings made of heavy elements, are direct products of our Milky Way's star formation and chemical evolution. The same processes have occurred in every galaxy. So the ingredients for life, carbon, water, energy sources, should be widespread. Life might have arisen independently in countless locales. It could be microbial, or it could, on some worlds, evolve complexity and intelligence. When we gaze at Andromeda, that large spiral many like to photograph, we are looking at possibly 1 trillion stars and perhaps several trillion planets. It would be the height of arrogance to assume none of those trillion stars hosts a living world. Perhaps on a planet orbiting a sun-like star in Andromeda's disk, beings gaze back at the Milky Way as a faint blur and have similar wonder about us. Yet, the distances are so vast, 2.5 million light-years between us and Andromeda, that any exchange of information is exceedingly unlikely, barring some science fiction-level technology. For all practical purposes, any life in other galaxies is isolated from us by enormous gulfs of space and time. Still, the idea that the universe could be teeming with life, consciousness, and even civilizations scattered among the galaxies is awe-inspiring. It transforms those faint smudges of light into potential distant homes. We have essentially no way at present to detect life in other galaxies. We can't resolve individual planets or even individual stars in most galaxies beyond our local group, except via special cases like gravitational microlensing events. But we can reason. The physical laws are the same everywhere. Chemistry is universal. There's nothing special about the Milky Way that would make it uniquely favorable to life. In fact, some researchers consider that large, active star-forming galaxies might occasionally have more hazardous environments, more supernovae, etc., whereas a quieter galaxy might be more benign. But life on Earth has endured supernovae and cosmic rays, so perhaps these are not strict barriers. One interesting point: galaxies with different histories might have different proportions of heavy elements, which could affect planet formation. Very metal-poor galaxies, like some dwarfs, might have fewer solid planets because heavy elements form the cores of terrestrial planets. The early universe's galaxies likely had only gas giants, if any planets at all, until first generations of stars produced enough metals. Now, in the modern universe, most large galaxies have enough metals for abundant rocky planets. So life's probability might have increased over time as the universe became more enriched. That suggests the universe may be more life-friendly now, at age 13.8 billion years, than it was at, say, age 2 billion years, simply because more chemical raw materials for life, like phosphorus, which comes from stars, or oxygen for water, etc., are available and planets are more common. If life is widespread, what does it mean for the cosmos? It means the universe has, in a sense, a way to know itself in many places. We on Earth are one small voice, but imagine countless others in distant galaxies, each observing their sky, maybe developing science, maybe sending out signals that will never reach another galaxy because of distance, but still, they exist. The universe could be filled with such points of light, intellectual light, one might say, each unaware of the others because of the enormous separations. It's a bit poignant. The universe could be bursting with life and intelligence, yet each island galaxy is mostly isolated, separated by oceans of space that likely cannot be crossed with communication or travel given known physics. It's as if each galaxy is its own closed ecosystem of life. If that's the case, then our efforts to find extraterrestrial intelligence might only succeed within our own galaxy, listening for signals, or perhaps one day sending probes to nearby stars. Contact with any intelligence in another galaxy is far beyond any realistic scenario. Signals would take millions of years, even if they were intentionally directed, which they likely wouldn't be, as there's no way for them to know we're here. So in practice, each galaxy's life forms must live out their existence without knowing for sure if they are alone in their galaxy, and certainly without direct contact with other galaxies' life forms. Nonetheless, just knowing that life likely exists out there can change our perspective. We can look at a galaxy cluster and imagine it may host billions of biospheres. It adds emotional depth to those points of light. It also humbles us. We are one tiny form of life on one planet, around one star out of 100 billion in one galaxy among billions. It's the ultimate Copernican extension. Not only is Earth not the center of the universe, our galaxy isn't either, and life, if common, is not centered on us. And if, by some chance, life is extremely rare, if it turns out Earth is one of very few cradles of life, then the burden on us is immense. We carry the flame of consciousness for the cosmos, perhaps a flame that flickers only in a few places.
That would make the universe a lonelier place, and our role all the more significant, to cherish and propagate life and consciousness. Either way, the mere possibility of life throughout the galaxies casts the cosmos in a new light, a possibly living cosmos, or at least a cosmos with many oases of life. After contemplating these sweeping themes, the birth and death of galaxies, the rise of stars and possible life, we return to the personal perspective. We live inside a galaxy. What does that mean? It means when we look up at the night sky, we are looking through the lens of our galaxy's stars. All the starry sky we see is part of the Milky Way, except a few smudges, like Andromeda. It means the story of the Milky Way is our story.
For a long time, humanity didn't know that those spiral nebulae out there were other galaxies. Only in the 1920s did Edwin Hubble and others prove that the Andromeda Nebula was far outside the Milky Way, settling the great debate and expanding our known universe enormously. Since then, our perspective has changed from thinking the Milky Way was essentially the universe to realizing it's one of countless universes within the universe. This awareness that we inhabit a galaxy among many is one of the profound intellectual revolutions of the 20th century.
So, to live inside a galaxy is to know that the universe is much larger than our home. The Milky Way is immense on a human scale. 100,000 light-years is far beyond direct comprehension. Yet we know now it's just one disk among billions strewn through space. That can make one feel small, but also connected to a grander existence. We know our galaxy's place in the cosmic web, on the outskirts of Laniakea supercluster. We know its future, merger with Andromeda, eventual fade-out. We've pieced together its past, formation from smaller pieces, multiple bursts of star formation, perhaps a barred spiral structure forming later on. Thus, we have context for our own existence. We're not adrift without a cosmic address. We can say we reside in the solar system, which orbits in the Orion arm of the Milky Way, which along with Andromeda and others forms the local group, on a filament at the edge of the Virgo supercluster. When the cosmos is remembering itself, part of that memory is our emergent understanding of our coordinates in space and time. We've learned that heavy elements in our bodies were forged in the Milky Way's previous generations of stars. Effectively, we are children of the Milky Way. In a poetic sense, the galaxy made us, and now through our eyes and minds, it has become aware of itself. We often speak of, we are the universe experiencing itself. At a more localized level, we are the Milky Way experiencing itself. Tiny, conscious bits of the galaxy that can contemplate the whole. This perspective can instill a sense of belonging and unity. All humans are literally of one dust, cosmic dust from our galaxy's past stars. The light of the sun that sustains us is a typical star's light in the Milky Way. The constellations that our ancestors named are patterns drawn on the backdrop of our galaxy's disk and halo. Our fate, as beings and as a planet, is tied to the galaxy's fate. If, say, a supernova goes off close by, or the galaxy's nucleus had a dangerous flare, it could affect Earth's biosphere. Conversely, what we do on Earth has negligible effect on the galaxy at large. We're too small. Except perhaps one day, life from Earth might spread to other star systems, and thus the galaxy would have a new phenomenon. Interstellar life, a kind of galactic ecosystem spanning multiple stars, originated by us. That remains science fiction for now, but in principle, a galaxy hosting a spacefaring civilization might see life expanding within it, in a way seeding parts of itself with purpose. To live inside a galaxy also encourages a cosmic perspective that can be spiritually significant to many. When we see pictures of billions of galaxies and realize each is full of wonders, it can make everyday problems feel smaller and inspire a sense of unity with the cosmos. Many astronauts report a profound shift in consciousness
the overview effect, when seeing Earth from space, a fragile ball in the vastness. Multiply that to seeing the Milky Way from an outside vantage, which we can only simulate in our minds. One would see our galaxy as a spiral among others, and Earth an invisible speck. This could foster a deep sense of the preciousness of our world and the absurdity of human divisions. We are all riding this great galactic spiral together. In a very literal sense, our lives are bounded by the galaxy. The night sky's beauty, that milky band, is a constant reminder of the greater structure we belong to. We can't easily travel outside the galaxy. It would take an unrealistically long time with current or foreseeable technology to reach intergalactic space, so we will likely remain an intragalactic species for eons, if not forever. Our voyages will be between stars, not between galaxies, unless some exotic breakthrough in physics occurs. But that's fine. The Milky Way has plenty to offer. Think of the diversity within one galaxy. We have regions densely packed with stars, like globular clusters where skies are awash with starlight. Regions almost empty, like the far outskirts where a star's nearest neighbor might be tens of light years away, a dark, lonely void. We have neutron stars, black holes, planets, comets, nebulae, bright blue giants, tiny red dwarfs, an entire zoo of cosmic objects, all bound by the common gravity of our galaxy. We have the relics of ancient history, old stars with virtually no metals, nearly as old as the universe, and the promise of the future, protostars in dusty cocoons that will light up soon. We have cataclysms, supernovae occasionally lighting up. The last seen in our galaxy was over 400 years ago, but surely more have occurred hidden by dust or on the far side. And we have gentle stability. Our sun has been shining steadily for billions of years in a fairly calm part of the galaxy. When we consider everything, to live inside a galaxy is perhaps the most profound scientific realization we have. It situates us in the vastness. It invites us to think on scales far beyond the human, and yet to marvel that our minds can do so. We have used mathematics and physics, products of human thought, to decipher the workings of the entire galaxy we live in and beyond. In doing so, we, who emerged from this galaxy's stardust, have closed a loop. The galaxy has given rise to beings who can, in a way, know the galaxy. Now our journey nears its end. We have traversed from the darkness before galaxies to the emergence of the first islands of light. We examined the anatomy of galaxies, their varieties and inner workings. We followed their life cycles and large-scale patterns. We pondered the interplay of stars and black holes, the webs that bind them, the winds that carry their essence outward. We imagined the presence of life within them and our own place on one tiny world, circling one average star in the Milky Way. It has been a vast journey, outward and inward at once. Let us end with a moment of cosmic contemplation. Envision our Milky Way as seen from a distance. Say, from a vantage point far above the galactic plane, a few 100,000 light years out. You see the great spiral suspended in blackness. Its disk is a gauzy whirl of blue and white, mottled with darker lanes. The central bulge is a warm golden glow. Encircling it all is a dim halo studded with globular cluster sparkles. Perhaps you see the Magellanic Clouds nearby, small smudges orbiting their parent galaxy. Beyond, a spray of other galaxies, the members of the local group, dot the void. Now imagine you are the galaxy, not seen from outside, but feeling from within. The combined gravity of billions of stars, gas clouds, and dark matter holds you together. You feel the slow rotation, 100 million years per turn, like the heartbeat of a cosmic being. You remember when you were younger and gas-richer, and bursts of stars lit up your arms. You foresee a time when you'll be blended with Andromeda into a new form. But right now, you simply exist in a steady state, stars forming at a modest rate, stars dying occasionally in gentle or dramatic ways, a vast collection of worlds and wonders within. Around you, the universe expands. but you and your local neighbors are bound in your dance. Time flows. Eons pass, though you measure time in rotations and orbits, not in human years. You have no mind of your own to comprehend all this, but a part of you, on a certain small rocky planet, has developed curious, self-aware creatures who are collectively reaching out with their intellect to understand the totality of what you are. Through them, through us, you, the galaxy, have attained a voice and a consciousness that can describe you. In a poetic sense, we are the Milky Way gazing upon itself with wonder. One galaxy, still turning in the void, carrying at least one species that can reflect on what it means. Multiply that by billions for all the other galaxies, and we sense a cosmos, perhaps filled with meaning, or at least ripe for it. The void is not empty. It is the stage on which galaxies spin and shine, each a cosmos unto itself. And so we leave our narrative with an image, a lone spiral galaxy drifting in silent darkness. It doesn't know we're here, but we know it is here. We, the cosmos contemplating itself, feel a sense of reverence. The galaxy's stars continue to orbit lazily. A cloud of gas collapses somewhere into new suns. A distant cluster in the halo slowly moves along its path. The central black hole waits quietly for its next meal. The galaxy in that image is our own, the Milky Way, viewed from an impossible perspective, a grand pinwheel of starlight and mystery. Everything we have ever known, every person, every tree, every ocean, every mountain, is part of that faint glow. That galaxy is our home, and one day, far in the future, all that will remain of us is maybe a slight alteration in one of its stars, or the whisper of a radio wave traveling outwards. But the galaxy will continue turning long after we're gone, carrying the legacy of all who lived within it, in the changed chemical makeup of its gas, in the artifacts left on some planets, or simply in the fact that for a brief moment, one of its countless stars harbored thinking beings who marveled at the sky. The camera of our mind's eye pulls back further, and now the Milky Way is just one of many fuzzy spirals in a cluster. Further back, the cluster is just one cluster among many against the cosmic web lattice. But let's stop there. Let's focus again on our galaxy, one galaxy, still turning in the void, serene and majestic. The light from its stars takes tens of thousands of years to cross from one end to the other. The faint glow extends outward, fading into the black of intergalactic space. It rotates imperceptibly slowly. To our brief lives, it appears almost eternal and unchanging. Yet we know it is dynamic and alive with cosmic processes. In the quiet of the cosmic night, our Milky Way continues its stately rotation. We, tiny sentient flecks on a minor world inside it, can close our eyes and feel at one with this great wheel of stars. In our hearts, we carry its story, from darkness to light, from simplicity to complexity. A story written in the language of starlight across the vault of heaven. As the galaxy turns, we find meaning not in being central or significant in size, for we are neither, but in understanding and appreciating the beauty and grandeur that surrounds us. This is our galaxy, our home, one of billions, yes, but uniquely ours at this place and time. It drifts through the cosmic night, still illuminated by the myriad fires within, still creating new light. A part of the cosmos that once was dark has become light and aware. And as we conclude our long journey, we can step outside under the real night sky. The Milky Way arcs above, for those fortunate to have dark skies, a spectral veil of our galaxy seen from within. Every point of that veil is a star, many perhaps with planets, some maybe with life. We stand here, consciousness emerged from a collection of cosmic particles, looking up and out. We feel the whisper of the galaxy's ancient memory in that band of light, and we whisper back our understanding into the silence. In that exchange, the galaxy's light entering our eyes and our minds decoding its story. The cosmos remembers itself. We close with that image of the great spiral, turning silently, carrying the echoes of its formation and the faint songs of whatever lives it has fostered. One galaxy, among countless others, continuing its journey through the dark. A wheel of fortune, a wheel of stars, forever spinning, forever moving, and in its own way, perhaps, forever knowing, through the living beings that arise and gaze out from within. The lights dim on our narrative, but overhead the stars of the Milky Way still shine. The story of the galaxies goes on, and we have been part of it. We are part of it, forever connected to the universe that made us. The spiral turns in the cosmic night, and we turn with it, children of the galaxies, awake and full of wonder. At midnight by the shore, the ocean seems to breathe. With each silent swell, the water edges forward and then gently retreats, as if following a cosmic lullaby. A broad silver path of moonlight stretches over the waves, shimmering softly. That silvery glow on the sea is sunlight reflected off our moon's face, and the rhythmic tug of the tides is no coincidence. It is the moon's gravity pulling on Earth's oceans, drawing them up and letting them fall. In this tranquil moment, the moon holds Earth in an unseen embrace, one hand shaping the tides, the other painting the night with gentle light. Our moon has always been Earth's steadfast companion, but it was born from chaos. In the violent dawn of the solar system, over 4 billion years ago, a young Earth was struck by a Mars-sized planetary body. This catastrophic impact tore part of Earth's molten mantle into orbit. Out of that glowing debris ring, our moon coalesced. At first, it was a searing ball of rock much closer to Earth than it is today. The newborn moon loomed huge in the sky, and the tides it raised were titanic, racing across the early coastlines. Earth spun faster then. A day was only about 12 hours long, but over eons the moon's gravitational grip on our spinning planet put on the brakes. The tidal tug gradually slowed Earth's rotation and, in response, nudged the moon farther away. Even now, the moon drifts about 3.8 centimeters farther from Earth each year, a subtle widening of the gulf. Yet the bond between Earth and moon remains profound. The moon is tidally locked to Earth, forever turning the same face toward us. When we look up, the features of the man in the moon are the same ones every generation of humans has seen. And the moon's influence goes far beyond the ocean tides. The moon's gravity acts as a stabilizer on Earth's axial tilt, keeping our planet's orientation steady. Without our big moon, Earth's axis would wobble chaotically due to the gravitational nudges of the sun and other planets. Climate might swing wildly. Ice ages and scorching eras could alternate in extreme fashion. Instead, thanks to the moon, Earth's tilt swings only mildly, about 23 to 24 degrees, giving us regular seasons and a long-term climate stability that has allowed life to develop in relative peace. Mars, by contrast, with only tiny moons, wobbles on its axis far more dramatically, a likely reason for severe climate fluctuations on that world. Indeed, Earth is unique among the inner planets in having such a large moon. Mercury and Venus have none at all, and Mars's too are puny. It's intriguing to consider that our moon may be one of the keys to Earth's habitability, a cosmic guardian against chaos. The moon's steady tug has also shaped life on Earth in other ways. In its youth, when the moon rode closer to Earth and tides were immensely high, the rhythmic flooding and draining of coastal areas may have helped spark life's origin. Imagine the primordial shorelines of a young Earth. Water rich in organic molecules washing over sun-baked rocks, then receding over and over. These rapid tidal cycles could have concentrated simple chemicals into more complex ones. Some scientists speculate that the moon's extreme ancient tides acted as a natural distillery and reactor, perhaps aiding the formation of the first nucleic acids, the precursors to DNA, RNA, in warm tidal pools. Whether or not life began there, the moon has continued to nurture Earth's biosphere. The gentle, twice-daily pulse of today's tides
creates dynamic intertidal zones, areas alternately submerged and exposed, which are crucibles of evolution. Marine creatures had to adapt to the changing water levels, leading to greater diversity. The rich tide pool ecosystems, teeming with life that must endure both wet and dry conditions, likely owe their existence to the lunar tides. Some biologists have mused that without the moon's tidal influence, Earth's coastal life would be far less abundant and varied. For humanity, the moon has been a source of wonder, inspiration, and guidance since time immemorial. It has marked the passage of months. The word month itself comes from the moon and lit up our nights. Ancient cultures wove myths around the moon, seeing in it gods, goddesses, or spirits. They tracked its phases and held festivals by its schedule. But it was only in the last few centuries that we truly began to understand what the moon is, and that it is not alone. In 1610, when the first primitive telescopes were aimed at Jupiter, observers were astonished to see 4 starry points near the planet that moved from night to night. These turned out to be moons orbiting Jupiter, the first discovery of moons around another world. It was a shattering revelation at the time, proof that not everything circles Earth. Our view of the cosmos suddenly expanded. Earth had its moon, Jupiter had its own moons, and by implication, the universe was not arranged solely for our benefit. Since that breakthrough, we have discovered moons in every corner of the solar system. Even small asteroids can have moons of their own. Astronomers have found asteroid pairs and triplets dancing together in space. It seems nature likes to form moons whenever it can. The general rule is, the more massive the planet, or the stronger the gravity, the more likely it is to gather or form moons. And nothing in our solar system is more massive than Jupiter, king of the planets. So it is fitting that Jupiter presides over a truly majestic retinue of moons. When we voyage outward to Jupiter in our minds, we encounter a miniature solar system of at least 95 moons, and still counting. 4 of them are giant, planet-like moons, the very ones first seen in 1610. These are the Galilean moons, Io, Europa, Ganymede, and Callisto, each a world with its own character. Imagine approaching Jupiter. You would see Io, Europa, Ganymede, and Callisto as bright orbs lined up around the gargantuan planet, dancing in resonance. Jupiter's gravity dominates them, but they also tug on each other in a cosmic rhythm, and their identities have been forged by that interplay. Io, the innermost large moon, is a world of fire and brimstone. It is slightly larger than Earth's moon, but there the similarity ends. Io is the most volcanically active body in the solar system. Its surface is a hellscape pockmarked with hundreds of volcanoes, some erupting lava fountains dozens of kilometers high. When NASA's Voyager 1 spacecraft flew by Io in 1979, it caught sight of an umbrella-shaped plume shooting into space, a volcano actively erupting in real time. Io's surface is painted in sulfurous colors. Sulfur and volcanic gases frost the ground in yellow, white, and orange hues, and black lava fields from recent eruptions dot the landscape. Lakes of molten sulfur glow in volcanic calderas. Gigantic mountains, some taller than Mount Everest, rise from Io's plains, formed by tectonic thrusting from below. Unlike our moon, Io has virtually no impact craters. Any that form are quickly buried in fresh lava or plume fallout. Io is constantly renewing itself. The driving engine of this activity is tidal heating. Io orbits extremely close to Jupiter, closer than our moon orbits Earth, and is locked in a gravitational resonance with Europa and Ganymede. Io circles Jupiter 4 times for every one orbit of Ganymede, and twice for every one of Europa. This resonance means Io's orbit is slightly elliptical, and as it swings closer to and farther from Jupiter, the immense gravity of the planet flexes Io's solid body. Imagine squeezing a rubber ball over and over. Io's interior is likewise kneaded by Jupiter's tidal forces, generating immense heat through friction.
That heat melts Io's interior and powers its prodigious volcanoes. In effect, Io is caught in a gravitational tug-of-war. Jupiter's pull and the tugs of its sibling moons have made Io into a tortured, molten world. It's a place of constant eruption, where the sky is often darkened by volcanic plumes and the ground is coated with sulfur snow. If one could hover just above Io's surface, one would see fountains of sulfur spewing upward, and perhaps lightning-like flashes as volcanic material interacts with Jupiter's magnetic field. Io is a dramatic example of how alive a moon can be when subject to extreme gravitational forces. Moving outward, the next moon is Europa, a world that, at first glance, couldn't be more different from Io. Europa's surface is bright and smooth, like a cracked eggshell of ice. It shines white with slight tan and reddish streaks. These streaks are Europa's signature feature, long, curving fracture lines, some thousands of kilometers in length, that crisscross the entire moon, often intersecting in complex networks. They give Europa the look of a giant marble veined with brownish cracks. When Voyager and later the Galileo spacecraft photographed these lines up close, scientists realized they resemble features on Earth's Arctic seas, ice flows that have fractured and shifted. It appears that Europa's surface ice has broken apart in the past, with pieces pivoting or moving slightly and then refreezing. Very few large craters mar Europa. Its surface is young, geologically speaking. All of this points to an astounding conclusion. Beneath Europa's ice shell lies a global ocean of liquid water. Europa, though smaller than our moon, likely holds more water in its hidden ocean than all of Earth's oceans combined. The same tidal forces that heat Io are at work on Europa, though to a gentler degree, warming its interior just enough to maintain a deep ocean beneath, perhaps 20-30 kilometers below the surface, and perhaps even occasional eruptions of water through the ice. The reddish-brown material lining Europa's cracks might be minerals or organic compounds from the ocean below, deposited on the surface when water squeezed up and froze. Hubble Space Telescope observations have even caught faint ultraviolet glows and blurs at Europa's limb that could be water vapor plumes, geysers like those on Saturn's moon Enceladus, but more intermittent. If those plumes are real, they offer tantalizing direct access to Europa's ocean. Europa's ocean is a place of enormous interest, because wherever we find liquid water on Earth, we find life. On Europa, the ocean floor might have hydrothermal vents, hot springs gushing upward from the rocky core into the seawater, potentially providing chemical energy that could support life forms. Europa's ice layer insulates the ocean from the deadly vacuum and radiation of space. In the utter dark beneath the ice, maybe there are Europan organisms thriving near warm vents, utterly oblivious to the alien sky above. We simply don't know, but the possibility has made Europa a prime target for future exploration. Already, plans are underway. A spacecraft, Europa Clipper, is set to launch soon, which will perform dozens of close flybys, mapping the ice and searching for plume activity. And scientists even imagine a future lander that could drill through the ice or sample fresh deposits. Europa epitomizes the concept of a moon as a world of its own, not a dead satellite, but a potentially life-bearing ocean planet in miniature. The third of Jupiter's big moons is Ganymede, and it breaks records. Ganymede is the largest moon in the entire solar system, bigger in diameter than the planet Mercury. If Ganymede orbited the Sun rather than Jupiter, one might have called it a planet in its own right. Ganymede is a mix of rock and ice by composition, and it has a unique distinction. It is the only moon known to generate a magnetic field of its own. Within Jupiter's immense magnetosphere, Ganymede has a smaller magnetosphere, a bubble of magnetic influence, carved out by Ganymede's internal dynamo. This implies Ganymede has a molten metallic core, likely iron, churning away to create a magnetic field, much as Earth does. When the Galileo probe measured Ganymede's magnetic field, it was a surprise. It hinted that Ganymede is far from an inert ball of ice. The surface of Ganymede tells a story of a complex geological past. There are dark regions saturated with craters, ancient terrain, essentially dirty ice that has been frozen solid for eons. Then there are lighter regions with intricate grooves, ridges, and patterns. Swaths of terrain that look like they were deformed or resurfaced later. These grooved terrains may have formed by tectonic-like processes. Perhaps the crust was stretched and new icy material welled up, or by tidal heating effects early in Ganymede's history. Ganymede likely also has a hidden ocean beneath its surface, although deeper down than Europa's. Galileo spacecraft data, and more recently, Hubble telescope observations of Ganymede's auroras suggest a conductive layer, probably salty water, lies between the ice crust and the rocky mantle. So Ganymede could have a sandwich-like internal structure, rock at the center, a layer of warm water or slush above that, then a thick, icy mantle and crust on top. Imagine the variety of environments within: a metal core with a magnetic dynamo, a deep ocean under high pressure, perhaps studded with ice sealing formations, and a surface that has seen ancient cratering and more recent geological upheavals. Ganymede even has a thin atmosphere of oxygen, extremely tenuous, nothing like what we breathe, but detected through its influence on Ganymede's auroral glow. This oxygen is likely produced by sunlight and charged particles hitting the surface ice, splitting water into oxygen and hydrogen. The lightweight hydrogen escapes, leaving O2 behind. It's another parallel with Earth, which has oxygen from life, whereas Ganymede's is from chemistry. If we could stand on Ganymede, with a spacesuit, of course, we might see Jupiter as a colossal presence in the sky, 3 times wider than our moon appears to us. And we'd feel the tug of Ganymede's magnetic field, interacting with Jupiter's, perhaps auroras in the sky, or a constant drizzle of particles falling to the surface. Ganymede is a transition point, a moon behaving in many ways like a planet, with a rich interior and history.
The fourth Galilean moon, outermost of the big ones, is Callisto. Callisto is a survivor from the ancient past, a world that seems to have done little internally for billions of years. Its entire surface is blanketed in impact craters, so many that they overlap and form palimpsests of one another. In photographs, Callisto appears as a mottled, brownish-grey sphere, with bright white spots marking the youngest crater rays. Unlike Io, Europa, and Ganymede, Callisto isn't part of the resonance dance. It orbits too far out to be in the 1-2-4 rhythm, and so it largely escapes the tidal flexing that affects the others. As a result, Callisto never heated enough internally to completely differentiate. Its interior may still be a mix of rock and ice, or drive major geologic resurfacing. It's often dubbed a dead moon geologically, but that doesn't mean Callisto is uninteresting. In fact, as a time capsule, it's extremely valuable. Its ancient craters and surface chemistry preserve a record of conditions in the early outer solar system. One enormous impact basin on Callisto, Valhalla, has concentric rings spreading thousands of kilometers, a frozen ripple from a colossal ancient collision. The sheer density of craters on Callisto's icy plains suggests that, for whatever reason, internal processes never erased them. Interestingly, some evidence hints that Callisto too might have a very deep, sluggish subsurface ocean, perhaps a layer of salty water more than 100 kilometers below the surface, indicated by how Callisto interacts with Jupiter's magnetic environment. But if it exists, that ocean is likely static and cold, a far cry from Europa's or Enceladus's. Callisto's surface materials have been chemically altered by ages of radiation and impacts, giving it a darker hue. It lacks the bright youthful luster of Europa or the dynamic volcanoes of Io. Instead, Callisto offers a tranquil, if desolate visage, a world that reached an equilibrium and then faded into long cosmic quiet. If one day humans venture to Jupiter's moons, Callisto might actually be an attractive base. Precisely because it's geologically inert and far from Jupiter's strongest radiation belts,
it would be safer and more stable for human outposts than the more active inner moons. These 4 Galilean moons, Io, Europa, Ganymede, Callisto, together form a kind of miniature solar system around Jupiter. 3 of them are in a resonant rhythm that ties their fates together, while the 4th stands just outside that chord, solitary and pockmarked. They taught us early on that moons can be as fascinating as planets, and in some cases, more so. Jupiter, however, has dozens of other moons beyond these 4. Most of those are much smaller, irregularly shaped rocks that likely originated as captured asteroids or broken off fragments of collisions. They orbit at various distances. Many ride in packs that share similar orbits. For instance, Jupiter has a gaggle of distant moons that orbit in the opposite direction of the Galileans and opposite to Jupiter's rotation. These are retrograde captured objects, names like Pasiphae, Carme, Ananke, and so on, each only a few kilometers across. They may be remnants of a once larger captured moon that got shattered. Closer in, Jupiter has some inner moons like Amalthea, Thebe, Adrastea, and Metis that are small, tens of kilometers, and orbit very near the planet, zipping around faster than Jupiter rotates. These inner moons actually help maintain Jupiter's faint ring system by supplying dust from meteoroid impacts on their surfaces. Amalthea, reddish and irregular, is large enough, 250 parsecs, to have been discovered in the 1800s by telescope, but the rest were unknown until space probes or modern telescopes found them. With every improvement in our observational capability, Jupiter seems to add another moon to its count. Each is a little world tugged into the giant planet's gravitational embrace. They illustrate how rich a planetary system can be. Some moons were born with Jupiter, like the Galileans, forming out of the disk of gas and dust around young Jupiter. Others were snagged later. From fiery Io, near Jupiter's blazing radiation belts, to lonely Callisto at the fringes, and the tiny rock clusters beyond, Jupiter's moons together create a cosmic ballet around the solar system's largest planet. 400 years ago, we learned not everything orbits Earth. Today, we know that around Jupiter, almost everything orbits it. If our eyes were keen enough, we'd see a second miniature solar system in our night sky, circling that bright point that is Jupiter. Leaving Jupiter's domain and traveling outward, we come to Saturn, the ringed jewel of the solar system. And Saturn too carries a great entourage of moons, different in detail from Jupiter's, but equally fascinating. Saturn's known moons currently number over 100. 83 had confirmed orbits by the end of the Cassini mission, and more have been found since. They range from giant Titan, which is larger than Mercury, down to tiny moonlets, only a kilometer or so in size, embedded in the rings. Many of Saturn's moons are icy, bright objects. Some are darker and likely coated in dust or organic material. They present an astonishing variety of appearances and environments, truly a cabinet of wonders. First and foremost is Titan, Saturn's largest moon and the second biggest moon in the solar system, after Ganymede. Titan is often described as a world with Earth-like traits, and for good reason. It is the only moon with a dense atmosphere. So dense, in fact, that at Titan's surface, the air pressure is about 1.5 times that of Earth's at sea level. Titan's air is mostly nitrogen, like Earth's, but laced with methane and complex hydrocarbons. This thick orange haze shrouds Titan's surface completely, so for decades after its discovery, Titan's face was hidden from view. In 2004 to 2005, however, the Cassini spacecraft and its companion Huygens probe lifted that veil. What they revealed astonished scientists. Titan has liquid lakes and rivers on its surface. It has weather, clouds, even rain. But it's far too cold on Titan, 179 degrees C on the surface, for liquid water. Instead, Titan's hydrological cycle is based on liquid methane and ethane. In Titan's skies, methane clouds gather and occasionally sprinkle methane rain. The rain falls onto an icy crust, water ice as hard as rock, and flows, carving channels and rivers that lead into lakes and seas of liquid hydrocarbons. Cassini's radar mapped seas near Titan's north pole.
great expanses of liquid methane-ethane, one larger than Lake Superior. Huygens, the European probe that parachuted to Titan's surface in January 2005, actually landed on a slushy floodplain dotted with rounded ice pebbles, presumably shaped by flowing liquids. It sent back images from the ground, a dim orange sky, and a horizon of smoothed ice rocks, and a clay-like surface that had been wet not long before. Huygens detected moisture in the soil, likely from a recent drizzle of methane. Titan's atmosphere and weather cycle make it uncannily like Earth in outline. There are even likely seasonal changes, with methane rainstorms more frequent in some seasons. Indeed, Cassini saw evidence of one-off torrential downpours causing flash floods and new dark areas appearing, presumably temporary wet spots. But Titan's water is methane, its rocks are water ice, and its sand is likely grains of complex organic material precipitated from the atmosphere. It's as if we have a frozen twin of Earth's past. Some analogies can be drawn to early Earth, though the chemistry is different. Beyond its surface lakes, Titan likely has more surprises underneath. Gravity readings and Titan's rotation suggest Titan hides a subsurface water ocean as well, deep below an ice shell. Thus, Titan might have two habitats: a frigid surface with exotic methane-based chemistry, and a warmer interior ocean of liquid water, perhaps mixed with ammonia, as antifreeze. While life, as we know it, would struggle on Titan's surface, too cold for liquid water, and in liquid methane, biochemistry would be very slow, the interior ocean might be more hospitable. We simply don't have the data yet to know. What we do know is that Titan is remarkably rich in organic chemistry. Sunlight breaking apart methane in the atmosphere creates a wealth of complex molecules that drift down as an orange smog. Titan's surface might be coated in thick organic sediments, a treasure trove of prebiotic chemistry, the kind of molecules that, on Earth, led to the origin of life. This makes Titan extremely compelling to scientists. It's why NASA is planning the Dragonfly mission, a robotic rotorcraft that will launch in the mid-2020s and, by the 2030s, arrive at Titan and actually fly in its dense air from place to place, exploring different locales, dunes, perhaps a dry lakebed, maybe even reaching one of the smaller lakes. Dragonfly will sample Titan's surface chemistry and assess its habitability, effectively playing the role of a wandering chemical lab on this alien world. No other moon has a mission like that on the books. But Titan, unique and complex, beckons us in a special way. It's not just a moon, it's a world with an atmosphere and weather, a cold mirror of Earth in the outer solar system. Saturn hosts another moon that has reshaped our understanding of where life might exist. Tiny Enceladus. Enceladus is a small, bright ice moon, only about 500 kilometers across, that orbits in the midst of Saturn's diffuse E-ring. For a long time, Enceladus was just a shiny dot. Then, in 2005, the Cassini spacecraft discovered that Enceladus is geologically active. At Enceladus's south pole, Cassini spotted enormous plumes of water vapor and ice particles gushing from fissures, nicknamed tiger stripes, in the moon's crust. Geysers on a moon that small. It seemed unbelievable, but there it was. Enceladus was spewing its guts into space. These cryovolcanic plumes form a giant thin halo of fine ice dust around Enceladus, replenishing Saturn's E-ring continuously. Cassini flew through the plumes multiple times, essentially tasting the vapor. It found water, of course, but also organic molecules, various gases, salts, and tiny grains of silica. Those silica grains were a crucial clue. They likely form when hot water reacts with rocky minerals. That implies Enceladus has a hot rocky core in contact with liquid water. In other words, hydrothermal vents on an ocean floor. Yes, Enceladus too has an internal ocean beneath its icy crust, a global ocean of liquid water sandwiched between the core and surface ice.
Enceladus is essentially an icy shell with a warm ocean inside and a rocky core that probably provides the heat and chemicals via tidal heating from Saturn's gravity, plus maybe some radioactive decay warmth. It's like a mini Europa, but in some ways even more accessible. Enceladus conveniently jets its ocean out into space for us. The ongoing geysers mean we could, theoretically, fly a probe right through and analyze for complex organic compounds, or even signs of microbial life swimming in Enceladus's ocean. Unsurprisingly, Enceladus shot to the top tier of possible abodes for life beyond Earth after this discovery. Visually, Enceladus is stunning. Its surface, especially in the south polar region, is young and shiny, continuously resurfaced by falls of plume snow. The tiger stripe fractures are warmer than their surroundings. Cassini measured their temperatures. They were much higher than the frigid 200 degrees C background, indicating heat leaking from within. During Cassini's closest flybys, it actually saw curtains of vapor and icy particles backlit by the sun, a sure sign of active venting. The plume extends hundreds of kilometers into space. It's estimated that about 200 kilograms of water vapor are lost every second through these vents, a huge amount for such a small moon. Yet Enceladus has likely been erupting for millennia or longer. Tidal interactions with Saturn, and possibly a resonance with another moon, Dione, provide energy that keeps its interior warm enough to maintain liquid water. The entire south polar region of Enceladus seems to be a geologically unique province, crisscrossed by young fractures and free of large craters, clearly a hotspot above the internal ocean. By contrast, Enceladus's mid-latitudes and northern areas are older and heavily cratered, suggesting that the activity is focused in the south. No one is yet sure why only the South Pole is active. One idea is that a past impact or uneven distribution of heat caused a sort of cap of warmth down south. Whatever the cause, Enceladus is essentially a natural space fountain, spraying its ocean into the void and giving us a direct glimpse into an environment that could be habitable. As a result, there is great eagerness to go back. Future mission concepts include an Enceladus Life Finder probe, or even a sample return that would collect plume particles and bring them to Earth's labs. If, one day, we discover microorganisms or biosignatures in those salty ice grains from Enceladus, it would rank among the most profound discoveries in history. All from a tiny moon that, not long ago, we assumed was inert. Enceladus teaches us that even small moons can be extraordinary.
Saturn's inventory of moons doesn't end with Titan and Enceladus. There are dozens more, each with quirks. One of the most intriguing is Iapetus, a moon of moderate size, about 1,470 kilometers across, that has a two-toned appearance. The leading hemisphere of Iapetus, the side that faces forward in its orbit, is as dark as coal, while the trailing hemisphere is bright as snow. This gives Iapetus a striking yin-yang look. One half of the moon literally 5 to 10 times darker than the other. The dark material is thought to be debris, possibly dust from Phoebe, a distant retrograde moon of Saturn, that splattered onto Iapetus, or residue of icy materials that sublimated and migrated away, leaving a coating of complex organics behind. In addition to its color dichotomy, Iapetus sports a startling physical feature, a colossal ridge running exactly along its equator, wrapping much of the moon like the seam of a walnut. Some sections of this ridge reach 20 kilometers in height. It makes Iapetus look like two icy halves stuck together. The origin of this equatorial ridge is still debated. One hypothesis is that Iapetus long ago had a ring of debris around it, perhaps from a collision, and that ring rained down along the equator, building up the ridge. Another idea is that Iapetus rotated faster in the past, with a shorter day, and the equatorial bulge froze in place when the moon's interior cooled and solidified. Then, as the rotation slowed, the bulge became a towering ridge. In any case, no other known moon has such a feature. Iapetus orbits far from Saturn, quite isolated compared to most of Saturn's moons, almost 3.5 million kilometers out, and takes over 79 days to go round. In the Saturnian sky from Iapetus, Saturn would appear small. Iapetus is a bit of a loner, a mysterious one at that. Another noteworthy Saturnian moon is Rhea, the second largest of Saturn's moons, about 1,528 kilometers across. Rhea is a heavily cratered, cold classic ice moon, but with a twist. In 2010, Cassini detected a very tenuous atmosphere around Rhea, composed of oxygen and carbon dioxide. This was the first time an oxygen atmosphere was found at a world other than Earth. Later, we discovered O2 on Europa and Ganymede 2 in trace amounts. Of course, Rhea's atmosphere is exceedingly thin. A human would not notice it, but its existence means that chemical reactions are happening at Rhea's surface. The likely source of the oxygen is Saturn's strong magnetic field trapping charged particles that constantly bombard Rhea. When these high-energy particles strike the icy surface, they can liberate oxygen from water ice, a process called radiolysis. The carbon dioxide's origin is less clear, perhaps from trace organics in the ice being oxidized, or from dry ice trapped in Rhea's water ice. Rhea's surface shows hints of ancient tectonics. Some wispy white streaks on the trailing hemisphere turned out, on closer inspection by Voyager in the 1980s, to be bright ice cliffs, likely fractures where subsurface cleaner ice pushed out. But overall, Rhea seems geologically inactive now. Intriguingly, a few years before the atmosphere find, there was speculation, based on charged particle data, that Rhea might even have a tenuous ring system of its own, a set of thin equatorial rings of debris. It would have been the first moon known to have rings. Follow-up imaging didn't conclusively show anything, and the idea remains unproven. If Rhea had rings, they would be extremely sparse. Still, it's a reminder that moons can blur the line between what distinguishes a planet, with rings and moons, and a moon. Nature is creative. Then there are Dione and Tethys, mid-sized moons of Saturn around 1,100 kilometers across. Dione has bright wispy streaks across one side, once thought to be ice volcanism, but actually they are enormous bright cliffs, revealed by high-resolution Cassini images, marking tectonic fractures where fresh ice was exposed. Dione likely had internal activity in the past. There is some evidence, gravity measurements. It might even have a deep subsurface ocean now, though not certain. Its surface shows regions where tectonic forces pulled the crust apart, creating canyons and letting cleaner ice resurface the area. Tethys, on the other hand, is very ancient looking, dominated by a huge impact crater named Odysseus that spans nearly 2/5 of its diameter, a colossal basin that almost shattered the moon. Tethys also has a giant valley called Ithaca Chasma, running roughly north-south for 2,000 km, possibly formed as the crust cracked during cooling or when the big impact occurred. Both Dione and Tethys are largely ice, and both are locked in synchronous rotation around Saturn, keeping one face towards Saturn always. These moons also participate in orbital resonances. Tethys is in a 2-1 resonance with a smaller moon, Mimas, and Dione in a 2-1 with Enceladus. These gravitational relationships help maintain certain orbital spacings and may have once contributed to heating, especially Dione's resonance pumping Enceladus's orbit. Mimas, the innermost of Saturn's major moons, just 396 kilometers across, is often noted for its appearance. One huge crater, named Herschel, forms a distinctive round gouge so large it makes Mimas look like the Death Star from Star Wars. That crater is about 140 kilometers wide. If the impact had been much harder, Mimas might have been split apart. The impact made the moon ring like a bell. Interestingly, when scientists measured Mimas's rotation, they found a slight oscillation that was difficult to explain. One hypothesis, still controversial,
is that Mimas might hide a tiny internal ocean or a weirdly shaped core, causing an unexpected wobble. It would be surprising, given Mimas's small size and heavily cratered, seemingly inactive surface, but the data haven't fully ruled it out. It's a reminder that even the most innocuous-looking moon could harbor secrets below. For now, Mimas is regarded as a solid ice rock ball, heavily cratered. Aside from giant Herschel, many smaller craters give it a dimpled look, and it serves as a gravitational shepherd of Saturn's rings. In fact, Mimas is responsible for clearing out the Cassini division, the biggest gap in Saturn's main rings. Its gravity resonates with particles there, in a 2-1 resonance, ejecting them from that orbit over time. So even a small moon like Mimas can impose grand structure on a planetary ring system. Beyond the major moons, Saturn boasts a zoo of smaller moons, each contributing to the complex ballet of ring and moon dynamics. Tiny Pan and Daphnis, for instance, are little moons that inhabit gaps within Saturn's rings, the Encke gap and Keeler gap, respectively. As they orbit, these moons act as shepherds, their gravity nudging ring particles and keeping the gaps open. Pan is particularly adorable. Images show it has a flattened shape with a prominent equatorial ridge, making it look like a flying saucer or a piece of ravioli. Likely, Pan has accreted a skirt of fine ring material around its middle. Atlas is another ring-adjacent moon with a similar look. Then there are Prometheus and Pandora, a duo that shepherd the narrow F ring from either side, their repeated pulls corralling the ring particles into a tight band, while also creating kinky streamers and gores in the ring as they tug unevenly. Janus and Epimetheus form a unique pair. They share almost the same orbit and actually swap positions every few years in a do-si-do, a gravitational dance of co-orbital moons. Such an arrangement is extremely rare. They essentially trade orbits each time they approach, ensuring they never collide. And Janus Epimetheus were the first known co-orbital moons. Farther out, Saturn has a collection of irregular moons, captured objects with inclined, often retrograde orbits, much like Jupiter's outer moons. One of these is Phoebe, a dark, charcoal-like body, about 200 kilometers wide, that orbits opposite to Saturn's rotation in a distant orbit. Phoebe is believed to be a captured Kuiper belt object, or something from that distant population, imported into Saturn's gravity well. Material from Phoebe is thought to be the source of the mysterious dark coating on Iapetus's leading face. Dust from impacts on Phoebe migrates inward and eventually splatters on Iapetus. In this way, moons can affect each other across vast distances through dusty footprints. Altogether, Saturn's moons form an elaborate system of interactions with the rings and with Saturn's magnetosphere. The Cassini mission, 2004 to 2017, gave us an intimate look at this system, and every moon it examined turned out to have something unique. Enceladus with its plumes, Titan with its lakes and thick air, Iapetus cut in two-tone, Hyperion, a sponge-like chaotically tumbling moon resembling a giant honeycomb, even tiny moons like Methone, which are smooth, egg-shaped bodies, perhaps covered in fluffy, powdery material. One comes away with a sense that the Saturnian system is a kaleidoscope of natural experiments, each moon a slightly different mix of ingredients and history. If Jupiter's moons are like a quartet of well-studied characters, Saturn offers an entire ensemble cast, some playing major roles, others cameos, all contributing to the dynamism of the planet's environment. Continuing outward, we reach Uranus, the ice giant tipped on its side. Uranus's extreme axial tilt, 98°, means its moons follow a bizarrely skewed path. They orbit around Uranus's equator, which is essentially vertical relative to the planet's motion around the Sun. So the Uranian moon system is like a tilted disk rolling along with Uranus. The 5 main moons of Uranus, Miranda, Ariel, Umbriel, Titania, and Oberon, are mid-sized icy worlds, all locked in synchronous rotation, showing the same face to Uranus, and all relatively dark,
They don't reflect as much sunlight as Saturn's bright icy moons do. We know comparatively little about them, as only Voyager 2 has ever flown past, in 1986, giving us single snapshots of each. But those snapshots revealed astonishing geology on some. Miranda is the smallest of the five, about 500 kilometers across, and the most bizarre. It looks as though a child tried to glue together mismatched pieces of planet. Parts of Miranda's surface are extraordinarily grooved and chevroned, giant coronae structures that have no counterpart elsewhere. One region has a huge V-shaped ridge and trough feature, nicknamed the chevron. Others have oval racetrack-like patterns of grooves. Alongside these strange regions are cratered highlands that seem more ancient. Miranda also boasts cliffs up to 20 kilometers high. The famous Verona Rupes is perhaps the tallest known cliff in the solar system. The current theory is that Miranda underwent partial differentiation and tectonic activity, perhaps driven by tidal heating when Uranus might have captured it in a resonance at some point, that caused it to nearly come apart, or at least shift dramatically. Another hypothesis, more dramatic, is that Miranda was shattered by a massive impact and reassembled. In any event, Miranda's surface is the most varied, patched-together landscape of any moon its size. Despite being so small, which usually means geologically dead, Miranda clearly experienced major upheavals. Now it orbits quietly, but it hints at an interesting past. Perhaps it was once in orbital resonance with Umbriel or Ariel that induced internal heating. Ariel and Titania show signs of relatively recent resurfacing. Ariel, especially, has fewer craters than Umbriel or Oberon, and has many large canyons and smooth, floored valleys. The bright cliff edges and the topology suggest Ariel's icy crust was tectonically active. Maybe it warmed and partially melted, repaving sections of the surface. Titania, the largest Uranian moon, about 1,580 kilometers across, has a network of rifts and faults, including the Great Valley, Messina Chasm, about 1,500 kilometers long and up to a few kilometers deep. This suggests Titania expanded slightly, as Ice 2 in the interior might have shifted to Ice 1, expanding volume, and cracked its crust. Both Ariel and Titania might conceivably hold thin subsurface oceans if there's enough radioactive heat inside, or if some ammonia is mixed in to lower the freezing point, but that's speculative. Umbriel and Oberon, in contrast, appear more ancient and heavily cratered. Umbriel is the darkest of the five, a charcoal-colored orb with an oddly bright ring on one crater, possibly a deposit of fresh frost from an impact. It seems to have been mostly inert for a long time. Oberon, the outermost major moon, has a mix of craters and some signs of geological activity, like a few large faults or graben. One of Oberon's notable features is a mountain sticking out of a crater, perhaps an uplift of ice from an impact. All five of these moons orbit in the same plane, and interestingly, that plane, Uranus's equator, currently lies nearly perpendicular to the Sun. This means during parts of Uranus's 84-year orbit, the moons experience 42 years of continuous daylight, followed by 42 years of continuous darkness. During Voyager 2's flyby, Uranus's south pole and the southern hemispheres of the moons were in full sunlight. The northern halves were dark. Now, decades later, the illumination has flipped. Such long seasons could affect the moons, for instance, causing subtle warming and refreezing of surface ices, movements of tenuous atmospheres, if any exist. One of the big mysteries left by Voyager is that none of Uranus's moons showed clear evidence of internal heating at present. Yet, given how unique Miranda is, and how Ariel and Titania have signs of resurfacing, one wonders if perhaps in the past, some resonances or tidal interactions, maybe when Uranus's spin axis precessed differently, or if the moons migrated outward, caused heating episodes. Beyond the Big Five, Uranus has a myriad of smaller moons down to 20 kilometers across, many discovered only in the past few decades by improved telescopes or by Hubble. They have whimsical Shakespearean names: Puck, Sycorax, Portia, Juliet, Cupid, etc. Some of the inner ones are in orbital dances that exchange energy and maintain spacing, similar to Saturn's ring shepherds. And like Jupiter and Saturn, Uranus also has a cohort of distant irregular moons captured into inclined or retrograde orbits. Uranus's moons are among the least explored in the solar system. No spacecraft has orbited Uranus to give them a closer look, but they present an intriguing case study. How does an extreme axial tilt affect the evolution of moons? They might have experienced tidal heating in the past. Miranda's crazed surface is evidence of something. Perhaps some still have liquid layers deep down. We just don't know yet. Future missions. A Uranus orbiter has been recommended by planetary scientists for launch in the 2030s. Will hopefully shed light on these sideways moons. Finally, we reach Neptune, the last of the giant planets, and here we encounter one of the strangest moons of all, Triton. Triton is unique among large moons because it orbits Neptune in a retrograde direction, opposite to Neptune's rotation, and at a fairly steep inclination to Neptune's equator. This immediately tells us Triton was very likely not formed around Neptune, but was captured. Triton is about 2,700 kilometers in diameter, similar in size and composition to Pluto. In fact, Triton is probably a former Kuiper Belt dwarf planet that strayed too close to Neptune eons ago and was snared by its gravity. The capture of such a large object would have been a violent event. Triton's original orbit would have been highly eccentric after capture, causing tidal friction that could have melted a large part of Triton's interior. Neptune's original moons, if it had a regular satellite system, might have been destabilized and lost in the process. Over time, Triton's orbit circularized and shrank due to tidal interactions. Today, Triton orbits Neptune in a close, tight retrograde loop every 5.9 days, and Neptune's gravitational grip keeps Triton's rotation locked. 1 Triton day equals 1 Triton year, always showing the same face to Neptune. When Voyager 2 flew by Neptune and Triton in 1989, it revealed an active and youthful surface that stunned scientists. Portions of Triton are a pinkish-white icy plains, others are a mottled cantaloupe terrain of fused depressions. Few impact craters were seen, implying the surface is relatively young, perhaps no more than a few 100 million years old in places. Most surprising of all, Voyager's cameras caught sight of dark geysers erupting from Triton's surface. In Triton's thin nitrogen atmosphere, surface pressure only 1/70,000th of Earth's, they saw black streaks arcing up from the ground and then blown downwind, likely by gentle winds. These were cryogeysers, probably driven by solar heating of translucent nitrogen ice on Triton's surface. Here's how it works. Sunlight penetrates a layer of clear frozen nitrogen, warms material a few centimeters below, and that causes sublimation, trapped gas, which then finds a crack to explosively escape, carrying darker particles, like soot or organic compounds, with it, which then fall and streak the surface. Triton, therefore, has active nitrogen volcanism of a sort, powered not by internal heat, but by external sunlight, a very peculiar mechanism, unique to Triton so far. Beyond those geysers, Triton's landscape shows signs of tectonic movement and perhaps cryovolcanic resurfacing in certain areas, dubbed smooth plains. Voyager saw what looks like frozen slurry that had flooded and refrozen, akin to lava fields, but of icy material. Triton is exceedingly cold, around 235 degrees Celsius, just 38 K. Its surface is composed of a mix of nitrogen, methane, and carbon monoxide ices, with water ice making up much of its crust and interior. It has polar caps of nitrogen and methane ice. Voyager saw a bright southern cap. It was summer in Triton's southern hemisphere at the time, and likely there's a northern cap now that the seasons have changed. Triton's thin atmosphere includes nitrogen, the primary constituent, a bit of methane, and likely some carbon monoxide. These can form thin hazes and clouds. Voyager actually observed a delicate pinkish haze, layers up to 30 km above Triton, likely photochemical smog from methane,
analogous to Titan's haze, but far thinner. This atmosphere can freeze onto the surface when winter comes to one pole or the other, meaning Triton undergoes a sort of atmospheric collapse and rebirth with its seasons.
Under Triton's surface, given its relatively large size and the likelihood of past tidal heating from capture, it's hypothesized that Triton might still have a subsurface ocean, perhaps kept liquid by residual heat and antifreeze like ammonia. If so, Triton could harbor conditions for life in that interior ocean similar to Europa or Enceladus, though we have no direct evidence of it yet. Over the long term, Triton is spiraling inward toward Neptune. Millions of years from now, very roughly 3.6 billion years, Triton may reach Neptune's Roche limit and be torn apart, possibly forming a spectacular ring around Neptune. But that is far in the future. Neptune's other moons are comparatively small and faint. Proteus, about 420 kilometers across, is the largest after Triton. It's a darkly coated irregular shape. Voyager saw it as a lumpy, heavily cratered object. It's so large that one might expect gravity to have made it spherical, but Proteus is right at the edge of that transition and apparently never melted enough to round itself. Proteus orbits close to Neptune, just outside the narrow rings Neptune has. Nereid is another interesting one. Discovered in 1949 from Earth, it has a very elongated orbit around Neptune, which suggests it might be a surviving original moon that was severely perturbed when Triton was captured. Nereid is about 340 kilometers in size and rotates chaotically. Then there are several much smaller moons discovered mostly in the 21st century, with help from Hubble and large telescopes. Names like Despina, Galatea, Larissa. Actually, Larissa was seen by Voyager. It's about 200 kilometers. And farther out, Halimed, Sao, Laomedea, Neso, etc., which are only tens of kilometers across or less. One tiny moon, Hippocamp, about 35 kilometers, was only discovered in 2013. It orbits very close to Proteus and may actually be a fragment knocked off Proteus by an ancient impact, a baby moon born from a collision. The fact that even Neptune, way out in the dim reaches, with its chaotic history, holds a retinue of at least 14 moons reinforces that satellite systems are a common part of planets.
Our tour of the solar system's moons wouldn't be complete without venturing to the very edge, to the dwarf planets of the Kuiper Belt, which themselves have moons. Pluto, once the 9th planet, and now the archetype of a dwarf planet, has a complex little system of its own. Pluto's largest moon, Charon, was discovered in 1978, and it's so big, relative to Pluto, half Pluto's diameter, an eighth its mass, that Pluto and Charon together orbit a point in space between them, like a binary planet. Charon's gravity has locked Pluto in place, just as Pluto's gravity locked Charon. Thus, Pluto and Charon are mutually tidally locked, eternally facing each other as they spin through space. A Pluto day equals a Charon day equals 6.4 Earth days, and that's also the time it takes for Charon to orbit Pluto once. From Pluto, Charon hangs at a fixed spot in the sky, or never rises if you're on the far side. From Charon, Pluto does the same. They are like two dancers holding an unbreaking gaze.
Charon itself is about 1,212 kilometers across, and before 2015 was just a fuzzy blob in Hubble images. The New Horizons flyby in July 2015 changed that, revealing Charon's surface in detail. We saw a surprisingly varied terrain. Charon's southern hemisphere is covered in large craters and older surfaces, while its northern hemisphere has a massive dark reddish-brown cap at the pole, quickly dubbed Mordor informally. Across Charon's middle is an enormous belt of chasms, a giant system of canyons and scarps stretching more than 1,000 kilometers, with some cliffs 7 to 9 kilometers tall. This tectonic trench system suggests that at some point Charon's interior expanded, likely as an internal ocean of water froze and expanded, cracking the crust above. When water freezes, it takes up more volume, and on a global scale this could push the surface outward, causing the moon's crust to fracture extensively. The result? Charon's face bears a dramatic scar of that event. North of this belt, New Horizons saw smoother plains with fewer craters, notably a region called Vulcan Planitia. This area might have been resurfaced by cryovolcanism, essentially ammonia-rich water that oozed up and spread out as a kind of cold lava, filling in craters. It could be that after Charon's ocean began to freeze and the crust cracked, there was some upwelling of liquid that created a renewed, smoother surface in places. Charon's polar dark region, meanwhile, is thought to result from gases escaping Pluto. During Pluto's long winter, its atmosphere collapses onto the surface, but during the relative warmth of perihelion, some of it escapes Pluto's weak gravity. Charon, orbiting nearby, can capture some of these molecules, like methane. At Charon's poles, during its long winter night, those gases freeze onto the surface. There, ultraviolet sunlight eventually chemically alters the methane ice into heavier hydrocarbons and tholins, complex organics with reddish color. Over millions of years, this process painted Charon's poles that deep red-brown hue. Essentially, Charon has stolen a bit of Pluto's escaping atmosphere and turned it into a paint for its own surface.
Pluto itself is a wonderland, a great heart-shaped expanse, Tombor Regio, of which the western lobe is Sputnik Planitia, a vast basin of nitrogen, carbon monoxide, and methane ices that is notably free of craters. This indicates it's geologically very young, perhaps less than 10 million years old. The surface there is divided into polygonal cells about 20 to 40 kilometers across, which appear to be convection cells. The nitrogen ice warmed slightly from below, churning very slowly like a boiling pot, albeit on a timescale of tens of thousands of years per cycle, bringing fresh material up in the center of cells and pushing older ice to the edges where it cools and sinks. This process erases craters and produces a constantly renewing icy plain. Sputnik Planitia is thought to sit in a deep basin, likely caused by an ancient impact. Intriguingly, this basin is almost exactly opposite Pluto's side that faces Charon. That hints that the basin is somehow heavy, perhaps filled with denser material or hiding a subsurface ocean, and that Pluto reoriented, true polar wonder, to place that heavy spot on the tidal axis facing Charon, as gravitational interactions prefer. One theory is that there is, or was, a subsurface ocean of liquid water underneath Sputnik Planitia, whose mass, or the way it responds to flexing, helped stabilize Pluto-Charon in their orientation. Pluto also has tall mountains, some over 3 to 4 kilometers high, made of water ice bedrock poking through softer nitrogen and methane ice terrain, and some of those mountains, like Wright Mons, have deep central pits, possible cryovolcanoes that erupted a slushy mix in the past. To the north of Sputnik lies a rugged highland of heavily cratered terrain called Cthulhu Macula, dark in color from tholins. There are also weird bladed shapes on some equatorial ridges, perhaps formed by sublimation of methane ice into spiky landforms. And Pluto has a thin, multi-layered atmosphere primarily of nitrogen, which, when backlit by the sun, gleams with blue haze layers. A delicate, ethereal sight, New Horizons captured as it looked back at Pluto after closest approach. Pluto's smaller moons, Styx, Nix, Kerberos, and Hydra, are much tinier, ranging 30 kilometers to 150 kilometers across, and irregularly shaped. They were likely born in the same giant impact that formed Charon. They orbit in a neat resonant hierarchy. Styx, Nix, Kerberos, Hydra are in a 1, 3, and 4, 5, and 6 sequence with Charon, approximately. Curiously, these little moons rotate chaotically. For instance, Hydra spins roughly every 10 hours, but with a wobble that makes the exact rotation unpredictable. This chaos arises because Pluto and Charon's gravitational field is constantly varying as they orbit each other, perturbing the small moons. Imagine trying to spin a top in a gravitational field that changes slightly in orientation. It would be hard for the top to keep stable.
so a visiting spaceship might find, say, Nix tumbling end over end rather than smoothly rotating on one axis. The surfaces of these moons are quite reflective, especially Hydra, indicating they're covered in relatively clean water ice. They likely formed from the outer bits of Pluto Charon's impact ejecta that coalesced into small bodies. All in all, the Pluto system provides a fascinating parallel to the planet-moon systems we've seen closer in. It's like a mini solar system in the deep freeze, complete with a binary planet and an entourage of tiny moons shaped by a cataclysmic birth and delicate gravitational interplay. We've gone from seeing the moon in our sky, singular and familiar, to realizing that even tiny distant Plutos have multiple moons of their own. Moons, we've learned, are everywhere. And that naturally brings us to the question of exomoons. Moons around planets orbiting other stars. We now know of thousands of exoplanets, and by sheer probability, many should have moons. In our solar system, 6 of the 8 planets have moons, and the 2 that don't are the innermost scorched by the sun. The processes that lead to moons, co-formation in disks around young planets, capture of passing objects, giant impacts that throw off debris, these should also occur elsewhere. For a long time, though, exomoons eluded detection. They are smaller and dimmer than the already faint exoplanets. But astronomers are clever. They look for subtle effects in the data. One method is to watch the transit of a planet across its star and see if there are extra tiny dips or a slight asymmetry that could be caused by a moon either leading or trailing the planet. Another method is to measure slight variations in the timing of transits. A moon's gravity will cause the planet to wobble as they both orbit their center of mass, so the planet might transit a few seconds early or late in a regular pattern, betraying the presence of a companion. In the past few years, tentative signs of very large exomoons have emerged. One candidate is a Neptune-sized moon orbiting a Jupiter-sized exoplanet called Kepler 1625b, about 8,000 light-years away. If that detection is correct, it's still debated. It's an utterly alien scenario. A moon that big, radius Hayamal the size of Neptune, there's nothing like it around our sun. It might almost be a binary planet situation. Another candidate, around the exoplanet Kepler 1708b, also seems to be a giant moon, roughly 2 to 3 times Earth's radius. Why are we finding only giant moons? It could be that our detection methods right now are sensitive only to very large effects. Catching something Earth-sized or smaller is at the edge of our capabilities with current telescopes. The large moons might also be rarer outcomes, maybe even remnants of a double planet capture, or a planet that kept a fellow gas giant as a moon. As of now, no exomoon is confirmed beyond doubt. These signals are intriguing, but require follow-up with perhaps the James Webb Space Telescope or future extremely large telescopes to verify. Scientists are also mindful of selection bias. A habitable zone Earth-like planet could well have a modest moon, perhaps like our moon, but detecting that is far harder than detecting a Neptune-sized moon. So we shouldn't conclude exomoons are all huge just because the 2 candidates are. It's like if the only fish you could catch with your net were the big ones. You might falsely imagine the lake only has big fish. Many researchers suspect that moons as a class are common and diverse out there, likely reflecting what we see here. Lots of small moons, some medium, a few very large relative to their planets. In fact, some exoplanetary systems might have moons larger than Mars, orbiting super-Jupiters, or multiple moons around a super-Earth. The hunt for exomoons is more than a curiosity about numbers. If exomoons exist in habitable zones, they themselves might be abodes for life. Consider a Jupiter-sized planet orbiting its star at the right distance for liquid water. Any large rocky moon around it could have Earth-like conditions, receiving light from the star and perhaps from the planet, reflected light, and experiencing tides that might be gentle or, if orbit is eccentric, enough to warm its interior. Science fiction has often toyed with the idea of habitable moons. Think of the forest moon of Endor in Star Wars or Pandora in Avatar.
Nature might actually offer such places. They could have day-night cycles defined not only by their own spin, but also eclipses by their planet. Imagine living on a moon where regularly the giant planet looms in the sky and periodically eclipses the sun entirely, turning day to an eerie twilight as the planet's silhouette and corona cover the sun, a spectacular sight and a normal part of the moon's rhythm. Tides on such a moon might be complex, pulled by both the planet and the distant sun. A large moon around a giant planet might also be shielded by the planet's magnetic field from cosmic rays, or conversely, bathed in intense radiation if the planet has strong belts, like Jupiter does, which would be harmful for life on Io or Europa's surface. The interplay of factors is complex, but the possibility expands the concept of a habitable zone. It's not just planets we should consider, but moons of big planets too. Future telescopes might detect exomoons by their own atmospheric imprints. For instance, if a moon has a big atmosphere and it transits a star either slightly before or after its planet, perhaps a sensitive instrument like JWST could discern a tiny spectral signature like oxygen or ozone separate from the planets. At present, though, exomoons remain a frontier, one of the few categories of celestial object in the modern era still without a confirmed specimen beyond our solar system. This will likely change as data and techniques improve, and when it does, we will have an even broader context for understanding our own moons. We might learn how common or uncommon arrangements like Earth-Moon are, or whether huge moons commonly form around super-Jupiters, or how often moons survive migratory upheavals that many exoplanets undergo. Each new moon detection will add a piece to the puzzle of planetary system formation.